Check. 1, 2, 1, 2.
Oh, Vadim is not here.
He's registering right now,
Okay.
but hopefully he will be there.
Should we wait 1 minute more or should we start?
I feel we can
Okay,
start.
so we are late. I'm sorry, it's my fault. I was so happy discussing work with some of you I met after a long time. So welcome to SLE. Welcome to Cascais, okay, to Lisbon, to Portugal, and especially to this conference, the 16th edition of SLE. So this is the map of Portugal. So we are in Lisboa, in Portuguese, and we are here in this part of Lisbon, in the way from the river to the sea, and this street there is considered one of the nicest road trips to do in Portugal, and we are also close to the westernmost point of continental Europe, that is the Roca that is over there.
Can you use this?
Yeah, I think, okay. And this is the second edition of SLE in Portugal. We organized it in Braga, in the north, that's where I come from, in 2011. Yeah, it's always a pleasure to be involved in SLE. So these are the people involved. So we are the 33 members of the program committee. And my name is João Saraiva, I'm a general chair. And the people who did most of the work are all the other faces, okay, especially Elizabeth and Thomas, who are the PC co-chairs of this edition, okay? We call for, as usual, for submissions in 4 categories. So research papers, new ideas and vision papers, the body of knowledge paper, and the tool papers, okay? And so most of the work selecting this paper were done by the PC chair, so I'm going now to pass the microphone to Elizabeth.
Okay. Hello, everybody. Thank you for coming. So SLE has this tradition of 2 submission rounds. So the first submission round give an opportunity to update and then improve and resubmit papers if necessary. So the first one for that was April, and then the final submission round was in July. We got 40 submissions overall. Not actually very many in the April call. Whether that was because it was a bit quick after the announcement, it's not clear. But overall, we got 40 submissions, and all of them were reviewed by at least 3 PC chairs. So there were 20 that we accepted, 15 research papers, 1 new ideas vision paper, and 4 tools papers that we're going to present today. So who's monitoring? Okay, yes, so it's organised in 6 sessions, so we're running a 2-day programme, and the session after this one is the shared Gypsy keynote, so that's downstairs, I think, isn't it, in room 14? Yes. But apart from that, then we have the language implementation now, and then after lunch we've got grammars and parsing, and then inference and automation, and then tomorrow they're doing live programming and debugging. Then we have the keynote from SLE, and then modelling and tool demonstrations. So if you're giving a presentation, please make yourself known to your session chair. The session chair is listed on the programme. Is that it? Are we done? Right.
Okay, good morning, everyone. So as many of you know, Gypsy and SLE are 2 very close conferences, and typically in the past years we had 2 shared days together. It's a bit different this year because there's only 1 shared day, which is today. But still, we will have 2 shared keynotes, beautiful keynotes, one for Gypsy, one for SLE. So the SLE keynote will be delivered by Krista Lopez from UC Irvine in the USA. She will talk about artificial languages are dead, long-live artificial languages. This talk will be tomorrow in this room at 11 a.m. And the other one we have will be given by Julia Lawal. Julia Lawal is a research director at INRIA in Paris, and she's mostly known for her work on the coccinelle tool, and she will be delivering her keynotes in the Gypsy room right after the first session at 11 a.m. So the room is room 14, and it's downstairs, so you have to go down to actually find this room. And we ask you to stick around after this session, because right after the keynote, we will deliver the awards, the SLE awards, as well as the Gypsy awards, actually. So stick around 12:10 or 12:20, we will be delivering the awards.
Okay, so this is the sessions with awards that Thomas just mentioned. We'll have a closing speech by Frederick on Tuesday at the end of our conference, around 5:20. Okay, so in terms of the organization, it's very easy. Just leave the door, and you have the coffee breaks and the lunch. So I can say, I can't help you in that respect, so easy. But today's dinner, I think it's hard for us to organize a full dinner that with registration that we had to involve SPLASH, and it was not easy to do it. So I think we can do it in a kind of informal way. We meet in city center, or we can do some. If you please contact us. If you feel that we have a list of people, we can compile it, and I can try to book a large restaurant in city center, and we have a dinner tonight. Yeah, we are open to organize such dinner for our community, also probably together with Gypsy as well. And that's it. We have to say. I think now it's time to start the first session. Thank you.
Is it still working? Yes. Okay, so we're still looking for the session chair for the first session, so I will replace him on the spot. The first session is about language implementation, and the first talk will be delivered by Luca Favalli. Luca, please, you can come.
Thank you. Okay, I'm short, so I will stick a little bit to the side. Thank you for the introduction. As you know now, I'm Luca Favalli, and this is a joint work with Walter Cazzola, which you can see there in the audience. I'm very happy to kick off this track, and I hope that in the end you will be too. But of course, today we're talking about language implementation, and in particular, modular language implementation. So we all know that language development is complex, and especially when we develop languages in a monolithic way. Therefore, our attempt is to improve reuse of existing assets across several languages to ease such a complex activity. A very popular approach in the recent decades has been language workbenches that can help modularize and compose languages to improve their reuse. However, language workbenches alone cannot solve the inherent complexity of some of the most complex language features, such as cross-cutting language features. Therefore, in this work, we tried to do the first steps toward solving this problem by facing one of the most prominent cross-cutting language features in language implementation. In this case, we talk about exception handling. In fact, exception handling is a cross-cutting feature because it impacts the entire language implementation. For instance, it can be caused by any statement, so we cannot foresee which statement will cause an exception. They disrupt the execution flow because you execute statement by statement, but then you may jump to another side of the program unexpectedly. And they can also modify the memory state. So you can see that there are many elements of an implementation that can be affected by the way the exception handling needs to behave. So our question is, how can we entangle this concern from other language implementation concerns without making any assumptions on the language implementation itself? So that the base language is unaware on how the language exceptions should behave, and also we can so that we can replace exception handling mechanisms at will and add new in a smooth way. To do so, we started from the very base idea of exception handling. In fact, most exception handling mechanisms share three common elements, which are a part of the program that causes the exceptional event, a part of the program that is executed to handle the event when the exceptional event is arisen, and finally, a part of the program that can actually reach the exceptional event and kick off the execution of the handler. So, our approach, our modularization approach, builds on top of these three elements in a fine-grained way, and the result is a conceptual framework made of 10 elements. In particular, we can see the memory layout, which in our case is a generic graph. Most commonly, you will see a stack in most language implementation, but for generality, we just assume it's a graph. An exception table, which is an area of the memory where handlers are stored. The handlers themselves, which are stored in the exception table, and then the so-called sections. And sections are basically the nodes within the memory graph, and they can either be normal if they are outside of the reach of a handler, or protected if they are within the reach of a handler. For instance, if you are outside of a try-catch block, then the corresponding code will be a normal section. If you are within the try-catch block, the corresponding code will be a protected section. Then we have the thrower. The thrower is the part of the code that raises the exception. The secure area, which is a shared memory area in which all the elements of this exception handling layer can store and retrieve all the information that is relevant to handle the exception. For instance, the exception object itself in Java. And then the two algorithms that are dispatcher and selector, which I will discuss briefly. And finally, the finalizer, which is a recovery procedure that is started whenever the exception handling layer fails to handle a thrown exception. So, given this architecture, how does it work? First, we have the normal execution in which the program executes normally, and sections, so nodes in the graph, are connected to the memory graph. Typically, in a stack memory, we can imagine we are pushing sections and popping sections from the stack until we find a thrower. And the thrower will store any relevant information within the secure area, starting the exception throwing part of the process. Then we have the exception carrying phase, and here you can see for the first time the dispatcher, which is basically a traversal algorithm for the graph. So the idea is that we don't know how the exception can navigate the memory, and we let the dispatcher decide how to do so. For instance, in a normal stack-based memory, the dispatcher simply pops elements from the top of the stack until finding a protected section. However, in some exotic language implementation, the dispatcher can be implemented differently to navigate the memory in another way. So the dispatcher navigates all the nodes until it finds a protected section, and when it does, it kicks the second algorithm that we call the selector, and the selector is in task of searching within the exception table for a viable handler for the given protected section and the given exception and the given reason exception. So to do so, the selector navigates all the handlers, all the compatible handlers within the exception table, and either it finds a match or it fails to find a match. In this second case, we resume the execution of the dispatcher, again in the same way until finding another protected section, again starting the selector until we actually find a match. If we find a match, then the handler is executed normally. Otherwise, we eventually end all the sections in the memory. In other words, the dispatcher will have no more nodes in the queue to visit, and when this happens, the dispatcher fails, and therefore we run the finalizer procedure, which is a procedure that can resume a viable memory state or simply turn off the application in a safe way. For instance, again, in Java, if we fail to catch the exception, we simply print the stack trace and turn off the application. So here's the recovery part. Okay, this process is to work properly must be coupled with a proper modularization technique, which is the core of this work, and also the part that lets us really separate the concern of exception handling from other concerns. So we divided the language implementation into 3 layers. First, the base language, then the exception handling language features, and on top, all the element of the exception handling layer that I showed you before. So for instance, in the base language, you have all the normal elements of a programming language, such as expressions, blocks, and the identifiers, with any dependencies among one another. In the exception handling part of the language implementation, you find all the language features that are in task of throwing and catching exception, handling them, such as exception ID, try, catch, throw. Here there's a node called can throw, meaning a statement that can throw an exception, such as a division by 0, but it doesn't do it explicitly. And these features can have any degree of internal dependencies. For instance, it's very natural that the try depends on the catch part depends on an exception ID, and so on. And finally, the exception handling layer that contains all the elements I showed you before. So the finalizer, selector, handler, dispatcher, and so on. In light blue, you see all the algorithms, and in darker blue, the data structures. So given these three layers to modularize properly, the main idea is that the base language must be unaware of the exception handling language features, and also the exception handling layer must be unaware of the exception handling language features. So the dependencies are structured this way. First, I would like to say that I'll resume later, sorry. In the exception handling language features, you have all the dependencies to the base language. However, you can see that there are no arrows in the other way around, so the base language features are unaware of the exception handling features, and the same goes for the other part in which the exception handling features are unaware of the elements of the exception handling layer. So in a way, you can replace all the language exception handling features by swapping this layer only without touching either the base language or the exception handling layer. Similarly, if you see on top, the part I skipped before, you see a lot of the internal dependencies among the elements of the exception handling layer. However, most are directed towards data structures. Therefore, as long as the data structures are the same, which is a reasonable assumption to assume that the exception, for instance, the memory layout and the exception table stays the same, then all the other elements can be swapped at will without affecting all the remaining elements. Finally, all the three elements are put together by interacting on the same memory layout. For instance, the base language will push and pop elements from the stack, and so will the exception handling layer. Okay. So to prove the applicability of this modularization technique, we created a library, basically, which is the Java exception layer that acts as an intermediate layer between the language implementation and the Java virtual machine. The idea is that the library does not assume anything and does not assume the structure of the base language, and instead everything can interact just by fixing some generic data types. In particular, we decided to use 5 generic data types, which are the type of the exception ID, the type of the section ID, the type used to express the variable names within the memory, the type used to express the variable types within the memory, and finally the payload, which is the content of the secure area data structures. So as long as these data types stays the same, so they are instantiated to the same concrete type, then all the components of the exception handling layer can be swapped at will and can be shared across several languages without any problem. Also, this library provides the most common data structures and algorithms. So for instance, we created a default stack and a graph for the memory layout, an hash table to contain the exception table, and in particular, this table maps a pair of section ID and exception ID to the list of all the available handlers. And the secure area is a generic wrapper that contains the payload type, and we can store and retrieve data from this payload. We also provide the default algorithms. For instance, the dispatcher is a traversal algorithm for the stack that iteratively pops elements from the top. The selector queries the above exception table to find an handler, and the finalizer dumps the stack to the user and stops the program. All these elements are connected and glued together using a template method that we called raise. And as you can see, the the actual implementation is very minimal. In fact, on line 7, we started the dispatcher to find any handler. Then on line 10, if we found an handler, then we execute it on the secure area. Otherwise, if we didn't find any handler, we run the finalizer. So the idea is very simple. And also, you can replace the handling algorithm simply just by swapping this piece of code and gluing all the elements of the exception handling layer differently. So to see if this actually worked, we performed an evolution scenario based on a JavaScript implementation written in the Neverlang language workbench. And these 3 stages are, first, the original language that used a custom memory layout and a custom exception handling mechanism. Therefore, it has nothing to do with the Java exception layer. The second part of the evolution scenario, we refactored the language implementation by removing all the custom memory layout, all the exception handling features, and substituting them with a data structure based on the Java exception layer. And finally, in the third step, we used this second version of JavaScript to add a series of exception handling mechanisms, such as the try-catch block, the finally block, and the throw statement that are fairly common, but also less common ones and unconventional ones, such as the retry and resume statements that are not present by default in JavaScript and that are also not supported by default by the Java virtual machine, but we could implement them using the modularization based on the exception handling layer. I assume you are familiar with retry and resume statements, but just to remind you briefly, for instance, if you meet a retry statement, you update the memory according to what you found in the handler. For instance, here you increment A by a value X, and then you X, and then you restart the protected section with the updated memory layout to hopefully being able to complete the execution without throwing an exception. So this piece of code simply throws an exception 10 times until A becomes equal to 11, and then you are able to complete the execution. So here you can see an example of an implementation of a language feature in JavaScript. For instance, here you can see that the exception handling feature is completely unaware on how the exception handling works. Simply, they call the raise method that I showed you before and passes all the elements that are basically strategies. And then the exception handling layer will handle the exception depending on how each element is implemented. You can also see here that we used that this part can be replaced very easily because each of the elements that is initiated with a $sign is declared in another language feature. For instance, here you can see the exception table and the secure area, and therefore the exception handling language feature itself doesn't have any idea on how these instances are implemented. And we can swap this part of the implementation to reuse the same language feature without a different selector, for instance, or a different dispatcher, or even a different memory layout. Okay, so these are the results of our experiment. You can see that in the step between the first version of JavaScript and the second version of JavaScript, we could replace the custom memory implementation with a new memory implementation based on the GEL library by writing just a few lines of code, specifically 369 line of code and deleting 71 lines of code. So that is very reasonable. But the most interesting result is the second column. In fact, once the memory layout is in place within the language, we can add exception handling language features just by creating new files and without changing any of the pre-existing code. So once the exception handling layer is in place, you don't have to change any of the implementation to add new language features, both traditional ones, such as the try-catch, and the unconventional ones, such as the erase. Okay, thank you. We also did another example, I will be brief here, on another language called loglang. And here is interesting because loglang is used to express logging tasks on files and doesn't have a memory layout nor an exception handling mechanism in any way, but we tried to create an unconventional exception handling mechanism based on the exception handling layer. For instance, here the backup language feature now throws an exception if the file to backup, which is foobar, does not exist, and the user is tasked to say if they want to create it before proceeding. So it's an ultimate recovery procedure. And as you can see, it's a very unconventional one for a domain-specific language. And although it's very simple, it was easy to implement. It required one class, 3 Neverlang modules, and 1 Neverlang endemics likes for a total of 77 lines of code. So very easy. So in conclusion, we discovered that an existing memory layout can be replaced with a memory layout based on the exception handling layer with very limited effort. And once it is in place, both conventional and unconventional exception handling language features can be implemented again with very limited effort and without affecting the pre-existing implementation. The refactoring itself is not based on the Neverlang language workbench because the entire library is written on Java, so that it could be used with other language workbenches too, as long as they can interact with Java, and but also by rewriting a similar library for another language. And the exception handling layer can also be used to create varied exception handling mechanisms for both general purpose and unconventional domain-specific languages. I didn't write it here, but I would like just to add that another goal would be to try to face other cross-cutting language features in the future to see if a similar modularization technique can also face those challenges. So I think I'm about in time. Okay, great. Thank you. I would be very pleased to answer any question.
Thank you, Luca. Do you have any question?
Yes, please.
Could you perhaps say something about whether there's any specific features of Java that you've used in your implementation and how hard it would be to re-implement in another language?
Okay. Possibly, okay, I used quite modern Java, but the Java specific features that I used are just the generic types and the functional interface, which again is in modern programming languages very common. So I think again. We only have an implementation for Java, therefore I cannot ensure it could work in any programming languages, but I'm pretty sure that it could be very doable. Yes?
If I already have an established ASL, could you assess how complicated or how complex it would be to throw your system
Okay, so for my experience at least, this is as hard as complex the existing memory implementation is. So if you have a custom memory implementation that is used all across your DSL implementation, and you have to replace every usage with a memory layout written in this, with this technique, then it may be very complex. However, if your DSL has minimal interaction with the memory layout, then you can easily swap your memory layout with this one, and then, as shown in the results, once the memory layout is in place, adding exception handling features is very easy. Okay, thank you. Yes?
So breaks and returns from functions in many languages also have this aspect of breaking the control flow. Would you derive those constructs in terms of this, or would you have them as separate features?
Okay. I think I would derive them as part of this architecture. Again, this basically a return is just removing one section from the memory, resuming the execution from the previous section, and you can actually implement this as a callback to the exception handling mechanism in quite a smooth way. In this case, however, you would have to assume that your memory layout only contains protected sections, because all sections are capable of capturing the thrown result of the function they called. So in this case, there's this slight difference. However, one thing that I forgot, or rather I didn't have the time to say, was that sections themselves are not implemented differently based on the fact that they are normal or protected. They become such by result of the presence of an handler within the exception table. Therefore, you don't really have to do anything to turn a section into a protected section.
Okay, thank you again, Luca.
Thanks.
Maybe there's a... Okay. J'espère. And the implementation of Python semantics and optimization, it will be delivered by Olivier Mélençon from the University of Montreal.
I swear I tried it, it worked 5 minutes ago.
Oh, it will work. C'est ton écran qui est là?
Non, c'est ça, c'est
Ok.
Je vais juste redémarrer tout de suite, je sais pas ce qui marche pas. Ça va prendre 2 minutes, c'est correct. Désolé pour ça.
Non, pas de souci. Là, on commence en retard.
J'en profite, je vais prendre une photo. Je voulais prendre une photo. Okay, smile, just while it starts. Thank you. First conference, that's a souvenir.
That's why you need the session chair, a real one. Okay.
Does that one work? I can use that one. Which do you prefer?
As you wish. Can you try this one?
Does it work?
No.
No? Does it work? Good. Okay. Thanks a lot. So I'm Olivier Melançon from Université de Montréal in Canada. I'm going to present today an executable semantics for faster development of Python optimizing compiler. And the co-authors for this paper are Marc Filet from Université de Montréal as well, and Manuel Serrano from Université Côte d'Azur in France. Okay. I want to start by giving a few motivation about our work. So we are working on optimization of dynamic language, and in the last few years, we've been working in particular on Python. And through writing quite a few implementation of Python, we came to realize across the years that every time we implement a new Python compiler interpreter, we just find the semantics to be really complex and really error-prone. And this is an optimization problem because all the time we spend on getting the semantics right, we just don't spend on doing optimization, which is our goal. So we came up with that goal of writing an executable semantic which will automate that process of implementing the first few steps of the semantics of Python, but we also want it to be reusable, so we can reuse it on every new implementation we write, and hopefully we want it to be somewhat performant. So this semantic is what I'm going to present today, and the talk will be in 4 parts. First of all, I'll give an overview of Python semantic. If anyone is not familiar with Python in here, who's familiar with Python? And Python implementation? Okay, yeah, so first part will be necessary. Then I'll show the executable semantic and discuss optimization with a partial evaluation technique which applies specifically to this semantics. And then I will finish with example of integration of this semantic in one of our compilers. 1 second, there we go. Okay, so first, why Python? You've probably heard that a lot. Why Python? Because it's popular right now on the TIOB index for this month. It's still first, once again, and it has somewhat uncompetitive performance. CPython is known to be slow, and it is known that it has a lot of superfluous instructions, such as method call, boxing and unboxing of primitive values, and a lot of type checks. And we have good implementations. For example, PyPy is one of the state-of-the-art implementation at the moment, but we still need better implementations. So why is it hard to implement Python semantic? Well, I'll give an overview of the semantic, and I hope you'll understand. First, Python is an object-oriented language, and in Python, everything is an object. And by everything is an object, we mean that everything has an ID, which is a unique identifier, a type, and a value. And I want to go deeper into the type. What a type is another object which has attributes, which are methods or functions, if you'd like. And depending on which function are on the type of an object, you will know which operations are allowed. So for example, for an object to be addable, so if you want to be able to do addition, it must have the double underscore add method. And you'll see that convention, double underscore something. This is how those methods that implement operations are called in Python. So let's give an example of what that looks like. If you have the operation 1 plus x, and say x is 2 here, how will Python compute the value of this expression? Well, first of all, Python will take the left-hand side operand and check its type, which is the int type, integer type in Python here. Then it will try to look for the add method of this type, and if it exists, which it does for the int type, it will call it with the left-hand side and right-hand side operands, and this will return 3. No surprise here. And this is actually an easy example because everything went smoothly. So the add method exists, And then the add method, of course, expects to receive an integer as second argument. So let's see what happens if we have a more complex example. We have the same expression, but this time x is actually a programmer-defined type with the class keyword. So the same happened at first. We get the type of the left-hand side, then we find the add method, then we call the add method, but then we have a problem because x is a programmer-defined type. So add doesn't know what to do with this method, and it actually returns not implemented. Not implemented is an object. Everything is an object in Python, but it's a special singleton which tells the semantic of addition, well, this method here, it doesn't know what to do with x. So what Python does, it falls back on the right-hand side operand, and here let's say x as type t, then it will go get the double underscore r add. The r here stands for reflected, so we fall back on the reflected addition method, and we call this method here. And hopefully it returns some result, and if it cannot, for example, if it returns not implemented, then we raise a type error, and we cannot do addition. And basically, all operation, arithmetic operation, unary operators, comparisons are done the same way. But the name of the method, for example, will change. So for addition, we have double underscore add, but for subtraction, we will have double underscore sub. And there is one last complexity which I need to mention. Well, Python supports inheritance and actually multiple inheritance. So when you do that method looking up for the add method on in, for example, you don't just look on the type, you actually have to look on the type and all of its parents. So there is this linear lookup of methods. And since types are actually objects and are mutable, you cannot pre-compute, in general, this method lookup to execute operations. And semantically, if you have a direct implementation of this semantic we just described, well, there is a significant overhead because we've seen just for addition of 1 and 2, we have one method lookup, we have one method call, and we did not talk about what happened inside the method call where the type checks and boxing and unboxing lie. So it's quite a significant overhead for adding 2 small integers. And we come back to that executable semantics that we wanted to write to be able to implement all that behavior that we've seen and just be able to reuse it, to have it in some format which we can reuse when we start an implementation. So what we did is we went on the Python official documentation here, and everything I've just described, that's what is highlighted in yellow. So this is from the Python official documentation, and our goal is to convert this into some form of reusable format that we can reuse across compilers. So the first attempt we had was to write that in pseudocode, at least to guide us. And here you have the implementation of this addition, which go get the add method and calls it. And there is the pseudocode implementation of the fallback on the reflected addition method. And we see that in the end, at the last line, if nothing worked, we raise a type error. So that's the pseudocode implementation. But we cannot reuse that, so we try to write it in plain Python so a compiler can just read it and integrate it. Our first attempt looked like this. So we define a Python function, which is called add, and it has 2 branches. So you have on the left, you have the add pseudocode, which correspond to the normal nested function, and the radd correspond to the reflected. And the trick here is to use the built-in function get attr in Python, which looks for an attribute or a method on an object, which here is the type of x, for example, and can take a default value which will be returned if it is not found. But there's a problem with doing that. Actually, there are 2 problems. First is the get attribute built-in function will have its own semantic. Getting an attribute in Python looks for the double underscore get attribute method and calls it. And that's actually not what's going on when you have an addition. You want to do a simpler kind of lookup, which is looking at the type and its parent for the method add. And we also cannot use none here because none could end up being an attribute. So this first attempt did not work. And what we found out to work was to add primitive to our implementation. So we still write it in Python, but we ask the compiler which wants to read this semantics to recognize some primitives. So you have two primitives on the left, which are class get attr, which does that lookup on the type and its parent. And this function here will return another primitive, which is called absent. It's just an object we can recognize by identity if it is not found. And this here actually works. If your compiler or interpreter can recognize those two primitives, you can make it digest this semantic and use it at runtime. The only missing part is the actual method. Some of the logic happened in the method, and we did not define those yet. But we found that we can actually use the same strategy, that is, say, well, we'll write the int type, for example, in plain Python. We'll just add a few primitives to manipulate native values in the host language. And here we have two primitives which we use, which are called int to host, which takes a Python integer and unboxes it to get the value in the host language, and int from host, which does the reverse. It takes a host value and it boxes it into a Python integer. And so the add method, what it does, well, it takes x, it takes y, checks that they are both integers, then we'll unbox them, add them in the host language. For example, we'll add machine integers and then box them back to Python. And this here is the semantics of Python addition of integers. So if we just recap, what we've done is we added 4 primitives, class get attribute, absent, into host, and in from host. And with that, we were able to get a semantic which can be, if an implementation has those primitives, which can be digested by your interpreter and used at runtime. And you can actually, and we've done the same for other operations, such as other arithmetic, comparison operator. We've done it for truthiness, subscription, attribute access, iteration. You can define all of those operations with this strategy, because all they do is just get some method, call it, and maybe return a result. The question now is, what about performance? And the answer is, well, at that point, there's no change, because we've shown where the type checks are, we've shown where the magic method are being recovered, but we did not remove them. And this is where partial evaluation of the semantic comes in. We at some point realized a key fact about Python, which is really handy. It's that, and this is the case for CPython, PyPy, so we take it to be part of the semantics. When you have a built-in type, its methods cannot be mutated. So I said that types are mutable, but that's only for programmer-defined type. And so there is this idea that if you have a built-in type, well, probably that some of those boxing and type check can be removed. And we can actually remove them. I'll give an example with our definition of the semantic of truthiness. So in Python, everything is either truthy or falsy. And in particular, when you have a container, such as a string or a list, it will be truthy if it is not empty, meaning it has a length which is non-zero, and it will be falsy if it has a length of 0. So suppose you give a string to the truth semantic here. What will happen is, at first, Python will try to get its _bool method, which will give its truthiness, but on strings, since it's a container, the bool method doesn't exist. So what Python does is it falls back on getting its length and check if it's 0. And this is actually done by calling a semantic in its own right, which is the length semantic. So the length semantic tries to get the length method, which exists on string, tries to call it, and calling it does this here. So we have an implementation of the length method of string. And what it does is just it checks the type of its argument, then gets the length with a primitive which we call string length to host, and then this length, it boxes it to a Python integer, returns it, and compare it to 0. But since we know that for built-in types, methods are immutable, Everything which is in red here, we actually don't need to do if we know that the object is a string. So we don't need to look for the bool method. We know that we're going to call the length semantics. And in the end, we know that it's just this line we're going to execute. And we're just going, on the left here, to compare the result of that to 0. So computing the truthiness of a string should just use this quick path here and compute this result. And actually, we can do slightly better. Notice here, the comparison, the not equal to 0, is comparing to Python integers. You can actually go a bit deeper, and there is a boxing which is not necessary here. You can do the comparison between a host integer and the host length, and then box that as a Python Boolean. And this here, on the bottom, is what we call a behavior. A behavior is a special case of the semantic without all those magic methods. It's a fast path when you know the type of your operand for some operation. And we can write them in Python, so the compiler can compile them and reuse them with a few primitives. But there are dozens of methods, dozens of types, so we cannot do that by hand, and the goal would be to automate that whole process we've been through. And this is where our partial evaluation comes in. We wrote a tool which is called Senpai for semantics of Python. I was also doing karate at the time, so I called it Senpai. That's the name. What it does is it takes an operator, which could be, by example, the operation for addition. It takes a type context, for example, that x and y are int and float, and it outputs the corresponding behavior. And the neat thing is that Senpai can do that only using 3 simple transformations, and it works with those 3 transformations for all operators. It does aggressive inlining of all method calls and semantics. For example, that call of length inside truth, we've seen earlier, it inlines it. It does branch resolution. Since it has type context, it can remove type checks, check that a result is not implemented, and check that a method is not absent. And finally, it can remove those redundant boxing and unboxing at the end. And what it will look like, you give it a semantic on the left, and Senpai will know that if x, for example, and y are both integers for addition, well, this class get attribute will always return int.add. It will always return the add method of int. And then we know that, well, int.add is not the absent primitive, so we can just prune out this branch. And then we know that we're calling int.add, so we just inline it. And on the right here, you see what we've seen earlier, that the add method with the type check on x and y, checking their int, and then unboxing them, then adding them. But in the context where we know that x and y are integers, we can also remove those type checks on the left, and we end up with that result is equal to the boxing, unboxing, addition, and then boxing back. And we know that this is not implemented, so we can remove the final branch right here on the left. We can remove the branch result is not implemented, and we get to this behavior. And we've just used those 3 transformations, and the neat thing is it works for all arithmetic, comparison operators, and so on, with only those 3 transformations for all numeric types. And the goal is then to use those behavior and integrate it into a compiler to see the performance we get. So first of all, I want to point out that those behaviors we generated are actually independent from the compiler. As long as your compiler is able to parse Python syntax, which it should be able to do, and it knows those few primitives, then you can just make it read the primitive, integrate it in the compiler. And what we've done is we have our own prototype of Python, which is called Zippy. And what Zippy does is it just reads all those behavior, compiles them, and when it executes an operation, instead of doing that whole method lookup and then calling the method, it just looks at the left-hand side type, look at the right-hand side type, and dispatch to the correct behavior, which was pre-computed. In terms of performance, that's what it looked like. So here, what you have is a comparison between Zippy, PyPy, and CPython. In green, you have Zippy. In yellow, you have PyPy, and CPython is the baseline. So here, we're comparing how much faster we are than CPython. So higher is actually better. And on the left, what you can see is that we are, for at least benchmark, which are very arithmetic intensive, we are not only way faster than CPython, on some benchmark we are faster than PyPy. On the right, still you can see that Zippy it's a prototype, it's a work in progress. There are some features which are not implemented at all, so it's not surprising that we see some not arithmetic intensive benchmark to be fairly slow. So I want to conclude quickly now that where we came from is that we found out that Python semantic is just really hard to get right when you write compilers. And it also has those redundant operations such as method calls and boxing and unboxing. So we wrote that semantics so that it is not only reusable across compilers, but it also highlights these operations which are redundant. And through partial evaluation, we can generate those behaviors, those fast path for an operation for some given type. And as I've shown in the last slide, it gives us a fairly good performance on arithmetic operations. In the future, what we want to do, well, we only implemented those that semantic and those behavior for arithmetic operation, and comparison operation, and truthiness as well, but we want to extend it to iteration, subscription, calls, and we should be able to do it because all those do is find the correct method and call it. We also want to apply type analysis to better dispatch those behavior, because right now in Zippy there is no type analysis at all. It's just operations which are locally optimized. And one of the methods we want to use is basic block versioning. We will be looking into that in the future. And finally, all those behavior right now are generated ahead of time when you build the compiler, and we are interested in looking at what it would look like to generate them just in time. So that concludes the talk. Thank you very much, and I'll gladly take questions. Yeah, we've had a look at Smalltalk, and we also know that even CPython does that in some occasions because just looking for the method for adding two integers, it's just way too slow. And yeah, so to answer the question, yes, we had a look at Smalltalk, and just to be specific about what we do, to get those results, we have those behaviors, and we know that some of them are actually called more often. For example, addition of two integers. So what we'll do is each type has an index, a unique index which represents it. And if we see that the index of the left and right operands are either two integers or two float, what we will do is we will inline so we will do speculative inlining of the behaviors for addition of integers and float. And otherwise, we have that big table, and you can take both indexes of those types and find where the behavior is. I don't know if that was the question, but thank you.
I was just wondering, Python is a strange language, one that you can use
So we're really using this trick that you cannot do that with built-in types. So we can only apply behaviors with built-in types at the moment because we know those methods will not change. And in the future, one of the interesting things to do would be to implement behaviors just in time with the known method which some programmer-defined type has. And what you can do is, if ever you detect that this method changed, you just de-optimize the behavior. But we could still generate, because most of the time methods do not change, you just have to de-optimize when it happens. So in a just-in-time context, there should be a way to do that. You just have to be ready for some de-optimization. I think what you're mentioning is one of the ideas we have with just-in-time generation of those behaviors, because right now they are somewhat really local. It's only a behavior for addition of two types, and you have some information that comes in, and you should know that when you add two integers, you get an integer out. And right now we don't even do that. So with just-in-time generation of behavior, what you should be able to do is you have x plus y plus z plus, you have an expression, you check the types beforehand, you generate the whole behavior for this complex operation, and then you can run that. So that's where we're heading with just-in-time behavior generation. I'll have to think about that. At the moment, I don't know. The direction we're really taking is trying to get that type information which is lost when we leave behaviors, but I don't know yet. I'll let you know next time.
Okay, thank you again.
Thank you.
Okay, so next is our final talk for this session. The talk will be given by Gwendal Junot from the University of Rennes and the INRIA. So, Gwendal, for you.
Okay. So, hello everyone, my name is Gwendal Junot, and I will present you my last paper, Adaptive Structural Operational Semantics, to joint work between the diverse team in Rennes, people from University of Amsterdam and McGill. So before talking about languages, first I want to introduce a bit about the software that we build with. So nowadays, software evolve in complex and changing environments, such as IoT or embedded systems. And we see more and more the need for dynamic adaptation to best deliver the services. So for example, Netflix adapt the quality of the video they send you, depending on, among other, your bandwidth. And so what we argue is that as a consequence, there is a need to provide abstractions for self-adaptation, not for when it's primary concern, like Netflix, where you want to tailor everything by hand, but when it's a secondary, but nevertheless an important concern. So the abstraction for self-adaptation is a problem studied in other communities, basically in the self-adaptive system community. And solutions have been proposed. So for example, there are multiple architectural solutions, such as the MapK loop, the 3D architecture, or the Morph architecture. And they also provide frameworks, such as DCL, executable runtime mega models, and Ponder2, which even have a DSL to define your self-adaptive system. But the problem is that if you want or have already a DSL to capitalize your domain knowledge, it can be difficult to integrate those architectural solution frameworks. So, as we know, DSLs are a tool for experts with the appropriate construct for the given domain. But if your domain does not have as a primary concern self-adaptation, you have to basically implement in the programs or in the systems your own self-adaptation, which, if you want to use frameworks or architectural solution, it requires re-implementation, for example, for frameworks, which can be tedious or even impossible in some case when you don't have the primitives in the DSLs. And that also requires expertise in self-adaptation from the language user, which is not always the case if it's not primary concern of the DSL. So as an example, I will talk about the small language named Roblong, which is a procedural DSL to program robot missions, which provide abstraction for robot sensor and actuator. And for instance, in this kind of DSL, what we might want to do is to adapt, for example, the robot speed to save energy. It's a classical trade-off that we may want to perform. And so if we have difficulties to use a framework or have to code that by hand, we fall back to kind of method programming where we have implementation of a kind of trade-off reasoning at the top, and after that you have the effects of this trade-off reasoning with different conditions, which can be error-prone and tedious. And for each system, you have to manually design adaptation that requires expertise to design, manual implementation of the trade-off reasoning, like I said, and to be correctly integrated within the code base, which is often not really easy. So the question is the end. Of course, if I'm giving a talk, the answer is no. So we did previous work on that with the SEALS framework, published at SLE 2 years ago. The idea of the SEALS framework is a framework to implement DSLs with self-adaptive operational semantics. What we mean by self-adaptive operational semantics is that your operational semantics will change at runtime based on the result of a feedback loop that will drive some adaptations of the semantic rules, basically. And in addition, this framework also provides modularity for designing this adaptation, so you can just decorrelate the creation of the self-adaptive DSL and the creation of the adaptation in themselves. So the way the SEALS framework works, basically you free the DSL user from implementing the feedback loop and associated trade-off reasoning and integrate execution variants, which are the adaptation. And for the DSL designer, you have modeling capacities for modeling domain concept and also to specialize the feedback loop and the adaptation process in general. But the problem is that it's mainly an implementation framework, so we cannot specify our DSL with that. And particularly, it became hard to reason about because basically Java implementation. So what we want and what I want to present today is ASOS, so Adaptive Structural Operational Semantics, which is a meta-language to specify and reason about such self-adaptable operational semantics. So ASOS is defined as an extension of MSOS, so Modular Structural Operational Semantics. So we based on MSOS because it's a meta-language to define operational semantics, which is the domain that we want to target, as a modular definition of semantics rule, which fits what we want to do with modular adaptation, and provide the ability to verify some properties such as determinism, completeness, or determinism in some case. So we extended MSOS with by providing additional adaptation rules and how to introduce them in the semantics of the language. And from this definition, we generate an implementation with seals that use the seal framework. So our approach is around the definition of the DSL, so the language definition using ASOS. You have to define mainly three things. So the abstract syntax with metamodel, your semantics rule with the ASOS meta-language, and you have also to configure the feedback loop by giving some properties of interest for the trade-off and resources. And basically, the operational semantics that you encode with ASOS is defined as a default semantic, which is the usual semantics for your DSL. Adaptation semantics, which is additional rules to adapt this default behavior, and point cuts to express when and where to weave these adaptation semantics. So let's talk a bit about the code right now. So this is an ASOS definition of some rules of semantics. So the first instruction is basically the model or where to import the abstract syntax. So the idea is that our syntax is presented as a meta model that we merge with another meta model that represents the dynamic information that we merge to have an execution meta model on which we can operate. And in addition to that, this semantic definition is composed of a set of semantic rules. So you have, for example, here the rule program, that is the root rule for our DSL, which define a conclusion as a transition between terms. So here you have the term program with a subterm command, and this rule result in another program with a new command that has been partially evaluated, and that has made progress. In addition to those, conclusions, you can provide some premises that help you either compute subterms or define a condition to call those rules. So, for example, the resolve keyword here is defining the section of the premise, and here we have a premise that said that if the command can progress to a new command, then the program has advanced also. So the idea is that if we can execute the command to a new state, then the whole program has advanced to a new state. We have two kinds of transition premise. So the first one, which is the classic one, we also have termination premise. So the termination keyword is to deal with abrupt termination in the semantics. So for example, if you want to implement a break, a return, or exceptions, you might want to stop the execution of the current control flow and just fall back to some rules. And so to do so, you have the termination keyword, which given as an output of the conclusion rule, will just throw and emit a signal of termination with some dynamic values. So here, for example, we talk about runtime errors. And in your premises, you can just catch that to manage and continue and fall back to another behavior. So for example, if you get a return, you can just get the value and say that the function returned this value. So in addition to transition premise, we provide bindings. That's the bind section is related to computing values and storing values, basically. So in this case, you have self.value. So this value is coming from the dynamic information that were weaved with the meta model. And the self refers to the assignment that is in the input of the rule. So basically, what we say here is that the current value of the variable which is assigned is the integer that has been computed from the expression, basically. And finally, we have the where clause, where you can express first-order logic conditions, allowing, for example, to know if you have to go into the then branch or the else branch of a if concept, for example. And so, in addition to those semantic rules, and so the semantic rules provided the semantics for the default semantics, but we can also express adaptations on top of those rules. So here is, for example, the definition of an adaptation module, which is approximate double, where we have mainly two kinds of things inside those modules. First, matching definition, which is the point cuts of our adaptation, where we have a structural matching over nodes, saying that we want to apply some rules at some point if we are in a subtree from an assignment, which has a varref, for example. And we can also express additional constraints through the where clause. So, for example, here we target an assignment where the value that is assigned to a variable of type float. And after this matching definition, we also can express adaptation rules. So adaptation rules are extended semantic rules. So the first thing that you specify here is the kind of adaptation. You have three kinds of adaptation: before, after, and specialized, that will weave the new rules inside the semantics before, after the specified rules or in place of the specified rules. So, for example, here the before binop right hand side specified that the rule binop left hand side to float that is defined after should be called before calling the binop right hand side rule, basically. So if we take a look, step back and look at the meta model, what I showed you is that we have a definition of adaptive operational semantics, which is for the default semantics composed of rules. Those rules contain at least one transition that represent the conclusion and the effect of the rules, and potentially some premises that express the continuation of the computation to child of the node in the AST, for example. We have also the different clauses, so the bindings, the condition, but also, I did not show, but we also have input and output that allow you to communicate with the outside of the language. So for example, input is for user input in the console, and output for example, printing in the terminal, for example. And the second part of the adaptive operational semantics is the adaptation modules that are composed of a match, one or more match clauses that define when to introduce the adaptation rules, and adaptation rules that can be before specialized or after rules, kind of adaptation that target one rules and define another rule. So now that we know a bit more about the syntax of the meta language, we provided some formal semantics. I will not go too much into the detail of that, but the core idea is that we have to decide if we apply an adaptation or apply the default semantics. And so the translation of those rules is basically saying that first you get the set of possible adaptation or activated adaptation that you might want to apply. And if you select the correct one given the matching that you have, if you have at some point one rule that one adaptation rule that, that can be executed, you call it, and if you cannot here, then you fall back to the default semantics, which is basically how we proceed. But if you want to have more detail, you can take a look at the paper where it's more clearly explained. So on top of that, we provide a translational semantics from ASOS to seals to be able to execute the semantics. So the idea is the same structure of rule from ASOS. We first generate GWARDs, which correspond to verifying that the current term is corresponding to the pattern, the input pattern in the conclusion of the rule, so that's the little one. After that, we check some conditions, so the conditions that were expressed in the where clause, and we resolve premise to check if the output of the premise is corresponding to the term. So, for example, you've seen before the output termination runtime error, so we'll check if it's correctly runtime error or not. If it's not, we don't call this rule, but another. And if all those checks are passed, we then enter the effects part, so it's really applying the rule. So we just call, we basically translate the input and get the information from the outside, compute the different bindings that we can have. Then we actually compute the term, the output term, which can be done in different way. So for example, you can just update the current node, or you can return a value. Same here, if you want more detail on how we exactly proceed, you can take a look at the paper. And finally, we manage some of the outputs. So for example, print statement. And inside this generated effect, you have the input point for the different code for the adaptations. So now we generate this code, but how that is executed. So the first part when you call a rule on a node is to perform the feedback loop to know if there is some adaptation. So you will first monitor, analyze, plan, and execute by selecting the different modules that can be applied with respect to the trade-off and the current context. And based on that, you will have the second part of the process, which is basically matching those activated adaptation modules to the current node to see if the node matches those adaptation, to sort out the applicable adaptation rules. And then after we enter the process of just checking if the rule exists and call the adaptation rules one after another and select in the case of specialize because we replace and not add just a new rule. So to evaluate this work, we provide some proof on top of the formal model that we provided in the paper. So basically, we check determinism and completeness of the semantics that we define using ASOS. And about non-termination, what we can do currently is that we can detect patterns that we know will provide, will cause, for example, race condition and cycle between adaptations. But we currently overestimate because, for example, the feedback loop, the concrete the feedback loop step are not yet modeled in the formal model. So, for example, we cannot detect if two adaptation rules would create a race condition, but they will never because their matching is the feedback loop made them never appear together, for example. In addition, on the more executable part, we check the applicability on the Roblong DSL by providing adaptation to a program to slow the motor speeds to save energy. And we observe correct adaptation behavior, and we also observe that when changing the trade-off and dynamically, we are able to adapt to the change in this context. So that is okay. And on the second experiment, we wanted to check the performance of that. So compared to manually implementing the adaptation process inside the Roblong program. So we made an experimental setup with a machine where we executed 30 times the experiment with 3 times with reboot to mitigate the effect of initial state, to try to have a proper setup. And the results are a bit, well, at first were strange because we gain actually speed. But our theory right now is that's probably from JVM optimization, because the feedback loop in our case, so using ASOS, is defined using Java, while in Roblong it's in Roblong. And so probably some JVM optimization help us in the performance here. So as a conclusion, the ASOS meta-language provides abstraction for defining operational semantics and their adaptations. We also provide mechanism for composing adaptation with the default semantics at runtime, so basically calling them. And we also provide support for verifying properties on those semantics. On the technical aspect, we provide the IDE tool support for ASOS in an Eclipse environment, generator targeting the sales framework, and we are also fully compatible with Xtext, which means that you can define your DSL in Xtext and just provide semantics as an ASOS semantics, and it should work. And the perspective of this work is that, well, first, evaluate the complexity of using ASOS, because it's declarative and rule-based language. It's not the same as expressing that as, let's say, a visitor pattern for implementing the semantics. So we have to assess the complexity of that. We also want to verify the correctness envelope, so the way that we constrain what are the possible adaptations that were present in SEALD that we do not make in ASOS, because we don't really know how to constrain rules right now in the way that we want. And we also want to extend ASOS to configure the feedback loops, which is basically what I said earlier when I was talking about disambiguating some detection in the non-termination. And we also want to use ASOS declarative nature to support SAL composition and make language composition, self-adaptable language composition. Thanks for your attention, and if you have any question.
Structural patterns that are not possible to express using the typical MSOS rule format. Have you proved that? No. Give a reference.
Okay, that's maybe not the right way to put it. The idea was, when we were writing this, is that if you want to have some property like dissimulation as a concurrence, your pattern just you cannot nest so much pattern, while our matching pattern can be arbitrarily deep. So that was the idea around that. By allowing this matching deeper, it cannot be represented using MSOS without breaking this property, and that's what we said.
features, but just from a behavior point of view. As Java is Turing complete, I would hope that, well, you can translate nearly everything which is feasible. Can you give an example what absolutely makes no sense to translate, and how would you deal with that?
You mean translate from Java to ASOS?
No, I think the other way around.
The other way?
So you have your ASOS rules and translate to Java, or did I get that wrong?
Yeah, that's basically what we do in the generator, in fact. And no, I don't see really any problem of generation.
Okay, but why is then this checking step if you can whether you can translate something?
By checking step, you mean the generated word?
It was a slide or two before, I think. There's no valid adaptation transition. Maybe I got that wrong.
No valid transition is that, for example, you have some adaptations that are active, and that are, for example, for the assignment, but you have an assignment. If we take, for example, the previous example, which is so long ago. So for example, here we target assignment that are type float. So you have a module that is activated, but is not matching, so we do not provide these rules. So we have to check if those rules are available when we are executing, basically. So that's what's in.
Thank you.
Okay, thank you, Bernard.
Okay, I promise you'll be able to get a well-deserved coffee in a minute, but just as a reminder, the next session will be in the room below this one, so it's room 14, and we will have Julia Lawal's keynote as well as the awards session. And I think that Benoit has a word to say about the dinner.
You can say it.
Or I can do it, actually, yeah. I just didn't check the slides. Okay, thank you, Benoit. So, as announced beforehand, so there will be a joint dinner between the Gypsy folks and us. You can scan this QR code. I think it's a Google form where you can register before noon to be there for the dinner this evening. So if you'd like to go to the dinner, please subscribe here, and then we will keep you updated by email on the place, the number of people, and every little detail. Okay, thank you very much, and enjoy the coffee.
so, so, et. Et, et, so, et, so, so, et, so, 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 et, 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 so, 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 et, so, et, 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 so, et, a, et, 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 so, 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 et, et, so, et, 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 a, et, et, so, t, 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 et, t, 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 un, 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 et, un, un, et, t, 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 et, a, et, 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 E. 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 So. So. E. 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 So. E. E. So. E. So. So. O. E. E. So. 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 Mm. So. E. A. E. 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 A. E. 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 A. So. E. 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 A. Check. E. A. So. E. E. Check. E. So. E. 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 Allo. E. A. 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 E. 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 Allo. E. A. E. E. Allo. E. E. Allo. E. A. E. 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 Mm. Mm. E. E. Allo. E. A. Som. E, E, A. E, E. E, A, A. Som. E, 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 E. Som. Som. E, E. E. Som. 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 E, 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 E. Som. 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 E. E. Som. 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 E. 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 Som. 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 E. E. Som. 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 E. E. So. 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 E. 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 Alô. Alô. E. A. A. E. Som. Hum? Alô. 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 E. A. Som. 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 E. 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 Som. Check. E. Som. E. E. A. Alô. E. 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 A. E. 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 Check. E. 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 A. Check. E. A. Check. E. A. Check. E. A. E. E. A. 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 E.
Right, everyone. Shall we start with this session? The next session is going to be about grammars and parsing, and we start with a paper about a reference GLL implementation, and by Adrian Johnstone from Royal Holloway University of London. The floor is yours.
Thank you very much. Nice to see old friends and collaborators in the audience. I'll start with some acknowledgements from our funders, and also I thought I'd put this picture up because actually Ilko took it a few years ago. It's a picture I like, and it gives me an opportunity to acknowledge my not co-author on this occasion, but usually co-author Elizabeth Scott, who's hiding back there somewhere. She's the program chair for this conference, which is why this is a singleton paper. This is an updated version of a slide that I show whenever I do one of these talks, and it's, broadly speaking, the history of generalized parsers as they're being used out there, and I'll elucidate. There's a lot of information on this slide, and of course I'm not expecting you to take it all in. The green bits up there are all GLL related, so that's really the topic of today's conversation. And there are some other generalized parsers. You might call this the Amsterdam branch here, and the London branch of GLR, and there are some other things here, Horsford stuff.
Adrian.
Let me just summarize by saying this.
Can I just stop you? Can you speak into the mic? Yeah.
Is that working? Yeah. I can see you already better. Okay, right. So, is that actually switched on?
There we go. Now I can hear it. This is why I wasn't using the mic, because I couldn't hear you. This is the summary. This is all you've got to take away from this slide. The stuff down at the bottom here, the near-deterministic textbook orthodoxy, that's what every undergraduate is taught, you know. Bit of LL parsing, bit of LR parsing, and they can just about pass an exam question, write the automata. And, you know, that's essentially parsing for most people. It all kind of stopped in the mid-70s. If you go and look in the reverse engineering world and in various other worlds, the semantics world, you'll find generalized parsers appearing. And that central branch there represents work mostly out of CWI Amsterdam. There's Ilko there, for instance, in '97. Now, our particular branch of GLR ends up with this binary right-null GLR parsing there, Acta Informatica 07. And that's the target for most of our work in generalized parsing, and we believe that's our fastest algorithm. However, I'm not aware of any implementations out there of BRN-GLR because, to be honest, it's quite dense and quite hard. Well, obviously, I have implemented it, but I'm not aware that anybody else has had a go at it, even though we think it's probably the fastest thing that you're going to find. So instead, we have generalizations of LL parsing, the stuff that's in green up there, and the paying proposition for GLL is that it's simple to understand. Now then, that leads us to a problem. The real purpose of this paper is to sort my inbox out, because we think GLL is really simple, but sometimes it seems most weeks we get a paper, we get an email from folks saying, well, we don't really understand what's going on. Can you tell me what's wrong with my implementation? Ooh, that's a really hard one, because the answer, of course, is no. Debugging someone else's implementation is a very intensive activity. Even worse, we quite often get emails from people saying, well, we implemented all of GLL and we chopped this bit out and it doesn't seem to have broken, so we don't think it's necessary. And that's really troubling, of course, because if somebody takes one of your algorithms and cuts a bit out, then they probably haven't understood what it was there for in the first place. This all came to a bit of a head in Athens, actually, at ETAPS in 2019, when somebody sat down for lunch with us and said, have you seen that Sonar Source blog post on GLL? And we hadn't. Had a look, it was nice. And in the middle of it, it said, it's great, but there isn't even a reference implementation. And I thought, I better do something about that. And that's what this paper is. OK, now let's just go through the rest of the world. OK, so you know, let's get back to the textbook orthodoxy. The emphasis there is on deterministic parsing, linear parsing, and here's something that goes very, very fast in a straight line and is my metaphor for, you know, your typical LALR parser. It's terrific if what you want to do is handle something near deterministic, but it's going to flip over if you drive it too hard. There are a welter of alternative technologies out there now, by which I include things like pegs and extensions of various kinds to near-deterministic algorithms, which are also fantastic, but are characterized by only returning a single derivation. And my metaphor for that is Formula One car, which is very fast, but it needs to go on a special surface, and it's always going to take one route. And if there's another way across the track, it's not going to take it. In fact, it's not even going to tell you that those other routes exist. What we need for many of our applications, in particular for semantics and the kind of thing that Judy was talking about this morning, we need things that are like this. Now, Land Rovers are slow and heavy and rather resource intensive, but they will go everywhere. And just to sort of really emphasize that, while this video is running, I'll give you some more justification. When I was writing this paper, I had a little poke around, and I found, actually somewhat to my surprise, that GCC, no less, stopped using generated parsers in about 2004, so nearly 20 years ago. And the front-end parser, according to what I read, I'm not a GCC developer, the front-end parser for GCC has been handcrafted for nearly 20 years. Now, we must view this as a retrograde step, because we're interested in systems which can be formally specified and analyzed, and a bunch of code purporting to be the front end for one of the most commonly used compilers. For it not to be in that category is quite alarming. And of course, what we would like to do is to put a proper generalized parser with a principal disambiguation in there instead. It's a good job the sound was switched off, by the way, because at the end of that little video clip, when that Range Rover finally gets over that extraordinary cliff, there is some swearing. Now, leaving aside utility and being able to reason about the correctness of these very important tools that underpin so much of our software infrastructure, there's also the other aspect of the science, which is not correctness, but which is performance. Now, the three graphs here that are in this sort of magenta color were generated for SPLASH in 2013 when we were in Indianapolis. It was the parsing at SPLASH mini workshop. And what I did there was I took what we call our torture test, which is this uncomfortable looking grammar up the top here, the one that says we're going to match a string of Bs, but we're going to do it in a particularly stupid fashion by introducing a heap of ambiguity. And we use this grammar a lot because it triggers the cubic worst case bound for most of the algorithms that we're interested in, and it's a one-liner. So if you've got a generalized parser, it's fun to throw this at it and see what happens. Now, those curves are all the same, almost, right up until you start looking at the axis labels. The x-axis is the length of the string. The y-axis is the number of seconds that are required to perform the parse for that length of string. And as you can see, the two at the bottom, one of them from 10 years ago, one of them from last night, the one in blue I ran last night, they're coming in under a second, but you can spend a lot more time trying to do these parsers if you want. Now, caveat, strong caveat, these are 10-year-old experiments. I have no reason to believe that those tools or any other are as slow as they were then. But the important thing is that 10 years ago, all three of these implementations were being used, so they were actually out there in the wild. They weren't just lab experiments, and yet they've got such wildly varying performance characteristics. And this is the other aspect of my inbox. It's not just, can you fix my implementation, or do you know why I get away with not doing this? But there's also the performance issue. And we've had some fairly notable software engineering outfits write to us and say, well, we built this thing, and look, it runs this fast. And then I send them something like that back, or some equivalent set of metrics, and it's a lot faster. And we often don't hear from them again. So we don't want that. We want take-up of this algorithm. So we also want to explain how we achieve some of the figures that we achieve, or at least build up to it properly. Now, there is a problem with the original presentations of GLL, and that is that really what's in the papers is a parser generator, not a parser per se. And the parser generator aspect of it puts another meta level in the explanation. And also that meta level is really kind of at machine level. There's go-tos in there, things that really are just anathema to a modern software engineer. And that does cause a lot of grief. So really what I've attempted to do is to strip GLL back to its absolute minimum, deliberately make it as stupid as possible, take out several of the optimizations that we built into the original presentation, to be honest, without even really thinking. We just chucked them in because it seemed stupid not to. So what we've got is the stupidest thing that really corresponds to GLL. And then the idea is that in a series of presentations, which begin with this paper and some extension stuff, which is already in the GitHub site, we'll begin to build it back up to something which is production level for what we're doing. And what I mean by that, if I just zoom back to the third slide, is all that stuff that's in green in the top 3 boxes there, and everything from full parser downwards as well. So there's a lot of variant papers out there, and that's another source of traffic in my inbox, because sometimes people pick up one of these papers and they haven't got the earlier ones, and they get a little bit confused. Now, obviously, I'm not going to go through the paper in this presentation, because that will just send everybody to sleep, especially in the after lunch slot, but I will give you the overview of what is in the paper, which of course you can read. I'm not quite sure where the proceedings are. I guess they're online somewhere. It's a long time since I've seen a paper proceedings. This is the outline of the paper for this meeting. There's some discussion, the standard discussion about notation to describe context-free grammars, and a slightly careful explanation of what I mean by a compiled parser and an interpreted parser. And essentially, compiled parsers are what come out of our traditional presentation of GLL, a set of templates that are fitted together into a piece of code which you then compile and run standalone. Well, that's the alternative way of thinking about things is to say, well, I'll have a data structure in memory which represents a grammar, and I'll have a fixed piece of code which traverses that grammar and then performs the actions. I guess in some contexts we call that a table-driven parser. That's the way YAC works. It's got a tabular representation of the underlying state machine in memory, and the actual parser itself is a fixed piece of code which doesn't change from one grammar to the next and just traverses that table. So we're going to be focusing on interpreted parsers because I believe they're easier to understand, and it's very easy to derive the compiled parser from an interpreted parser when you have it. So the rest of the front material looks at our grammar representation, which I'll outline to you in a moment. It's very straightforward, and talks about just how much context a context-free parser actually needs. There are 3 algorithms that are presented in the paper. I start off with a backtracking recursive descent parser, which has got no smarts in it at all. You know, we've all used parsers, and nearly everybody has written a parser, and the classic parser that all of our undergraduates write is a recursive descent parser with first and follow sets in it. Well, we could go one step back from that. You could do away with the first and follow set computations and simply have a straightforward backtracking mechanism. And that's what I do with my undergraduates. I show them that as the simplest thing I can think of, which is a parser that does something useful. What I do in the paper here, though, is I start from the traditional compiled presentation and move in a couple of steps to what I'll call a state-based interpretation, which has essentially exactly the same shape as the interpreted GLL presentation that I then give in this algorithm baseline, GLL-BL, which I'll show you in a moment. So GLL-BL, like all GLL algorithms, maintains 6 sets. And when it's running, it's essentially building these sets. They only ever get bigger. You never remove anything from the sets to first approximation. We'll get to that in a moment. And these sets, between them, dominate the performance of the algorithm because these set updates and set lookups are essentially most of the computation that's performed inside GLL. Therefore, the performance is absolutely critically controlled by the efficiency of your set representations. Now, the 2 variants of the algorithm that are presented in this paper are called GLL baseline and GLL hash pool. So GLL baseline uses the standard Java APIs, and the intention there is that it'll look very familiar to any conventional Java programmer. They're not going to get freaked out by it, and they should be able to read the code and see exactly what it's doing, and very quickly come to the conclusion that actually it's not doing very much. The problem with that is that the Java API, well, you need to understand that on a reasonable parse, these parsers can easily generate millions of little objects. And the object allocation overhead in Java, as in all OO languages, is non-zero. And so the GLLHP version, the hash pool version, basically uses handcrafted memory management in a sort of very low-level C style to improve the performance, and it makes a huge difference. Okay, let's just give you a very brief overview of how this algorithm works. The idea is you take your grammar, there's a very simple grammar with 2 non-terminals in it, and you split it up into fragments which roughly correspond to the basic blocks of a traditional recursive descent parser. So for instance, you'll see in orange there, terminals, and where you've got a run of terminals, that's going to be a single fragment. Where you've got a non-terminal, that's going to be a single fragment. And in this presentation, there's a special fragment called end that is shoved onto the end of each alternate, and there's a left-hand side fragment which is shoved onto the front. How does that play out in code? Well, there's the same grammar and the same pictorial representation at the top, and underneath it, you can see a rendering of the data structure that is used by these algorithms. The reason why it's important to show this is because these are interpreted algorithms, and what they're going to do is they're going to traverse those data structures during the parse, and so we need to be very clear about how they're built. In the classical presentation, we use a higher level of abstraction and quite a lot of mathematical notation, which is a little bit tricky for some programmers, and we talk about the concept of a slot, which roughly corresponds to the dot, the Knuth-style item in an LR parser. Here, the slots are absolutely explicit, and we call these things G nodes, grammar nodes. And you can, I think, quite quickly see what's going on there. Each G node has got a unique number. It has a type, which is something like T or N or alt, and is actually an element of this enumeration down here. And each of these G nodes, here's the declaration, has then that unique instance number. It has a type, which is an element of that enumeration, and it just has 2 references, alternate and sequence, alt and sec. And the alternate, in the visualization here, the alt pointers are represented by horizontal arrows, and the sec pointers by vertical arrows. And then there's a special case of the end nodes. With the end nodes, the alt pointer points to the enclosing bracket, and the sec pointer points to the head of this sequence. You can see 23 and 24 there in that first production of X. It's very straightforward. It generalizes trivially to EBNF. As soon as you've got bracketed constructs like these red ones down here, so do first, parentheses, optional, that's the question mark that you'll see in the external syntax, positive closure, clean enclosure. Those brackets then become the thing that the alt pointer points back to. It's trivial. It's meant to be trivial. If you're looking at this thinking, God, this is pretty straightforward, Adrian, then I win, because that's exactly what I want you to think. Now, we talked about these 6 sets, and the sets work as follows. Essentially, GLL is a sequentialization of a piece of parallel processing, and we have thread descriptors which contain the context, and that's what class descriptor does. We need a graph-structured stack in the traditional manner for generalized parsers, and that has nodes and edges, and they're declared, as you can see there. The pop set, as it's presented in our classical papers, is distributed over the GSS nodes. In classical GLL, we had a single pop set with a set of pairs, and then the derivations are handled with shared packed parse forest and packed nodes. All the details are in the paper. Now, this is the filling in the chocolate. That is GLL written for Java programmers. And what I hope you can see is that the routine initializes, and then there is a labeled while loop called next descriptor, which attempts to dequeue a descriptor, and that's activating a processing thread. And then it runs around in a little loop. It switches on the kind, that's the type of the descriptor element that's coming out. And if it is a built-in or a terminal or a character, then it checks to see whether the input element matches. If it does, it updates the derivation, du of 1 there, and then it increments the input pointer, and off it goes. If it doesn't match, we abort this thread of control, And we do that simply by doing a continue on the next descriptor. So this thread of control is just killed dead, and we flip back up to the top of the loop. Non-terminals are trivial. We have a routine called call, which is analogous to a recursive descent call in a traditional RD compiler. And then when we come back from it, we continue with the next descriptor. If there's an epsilon, it's rather similar to a terminal, except we don't bump the pointer. And if there's a return, which is what happens at the end, then we do some processing in ret and then again continue with the next descriptor. So this is the outer control loop, if you like, for GLL. This particular version that's on the screen at the moment is extended over the paper version in that I've added the necessary cases to do parentheses and subrules, alternates within parentheses, and that's what it looks like. So we call that parenthesized BNF. I'm not going to go through all of this, but those are the bodies of the call and return function. The thing that I really want to flag up to you is the stuff in yellow is the stuff that everybody cuts out because they don't understand what it does. These are the so-called contingent pops. What's going on here is that when a non-terminal returns, when you return from a non-terminal, you need to remember that you've done that because you may do another return in a later context. And at that point, you're going to have to reactivate the return points from the earlier context. And this is by far the most subtle part of the algorithm. I would go so far as to say it's the only subtle part of the algorithm. And this is where people trip up. Okay, moving along quite quickly. Let's talk about memory management. So the problem with all those little nodes and set elements is there's millions of them, and it kills the Java allocator. A Java allocator does far more work than it needs to because it wants to do garbage collection. But these sets only ever expand to first approximation. And as a result, we can sidestep all of that, and we can allocate great big lumps of memory, and then simply say, well, OK, I need space for 6 elements now, so I'm just going to go and grab it by incrementing the pointer. And if the pointer falls off the end of a block, I'll just allocate another one. And that way, we can reduce the number of calls to the allocator by whatever figure we choose, a couple of million in this case. And it's transformational as far as the performance is concerned. And I think the lack of this kind of optimization is the thing that trips people up in terms of speed. OK. There are a lot of variants, which I won't go through here because we're short of time, but these are all published variants of GLL which need to be fully characterized and are not in this paper because it's a 12-page conference paper. But the good news is there's a big technical report on the GitHub site which starts with this paper and is building up and will continue to build up to handle each of these, including our most recent publication, which is the multi-GLL, multi-parser, which came out in Toplas a month or two ago. Frankly, they made such a mess of the typesetting that we're still arguing with them about it, but it is on the website and you can read it now. And it's very important if you're interested in lexical ambiguity. This is my last slide. Is any of this worth having? Well, I've got this kind of rule of thumb that I call GEG, good enough for GNU. I've got this kind of notion that let's assume that the parsing front end for GNU executes in 0 time. If you replace that with one of our parsers, what would feel like an unbearable slowdown? And the rule of thumb that I'm using is that if you dropped a generalized parser in and it only slowed things down by 10%, people might live with it. I hope so, anyway. So this is one example. Now, it's a very large example, but that's deliberately so because GLL runs cubic, worst case, and I want to show that this is valid even over very large lumps of source code. So nearly 120 kilobytes of source code there. It takes 18.8 seconds to go through GNU if you've got full optimization on. The current GLL HP, this very brain-damaged algorithm that is in this paper that doesn't have any of the optimizations in it, will rip through that in 1.35 seconds if you use the ANSI-C grammar. If you use the ANSI C++ grammar, it jumps up to 7.02 seconds, which immediately tells you quite a lot about the amount of ambiguity in C++ versus ANSI C. And as we know, ANSI C, of course, is not ambiguity-free either. So we're kind of getting there. I agree that 7.02 seconds is greater than 10% of 18.8. You know, I can remember enough arithmetic to do that. But there are a whole bunch of extensions, variants, and optimizations to apply. And our goal is to get that figure for these interpreted parsers down to a couple of seconds. And at that point, we would claim that even our interpreted parser is actually something that's viable for these, this kind of production work, never mind the kind of work on semantics and checking that we heard about in the keynote this morning. Okay, I think that's it. Oh, there is one last slide. Here are some GitHub repos that you should go and have a look at if you're interested in this stuff. All of the code associated with the paper is in the top repo. It is going to carry on being developed, and I guess I ought to put a tag in there to represent today's effort. We also did some work for TopPlus with very large corpora for Java 18 and standard ML, and the grammars and all of the test strings, thousands of them, are in that GitHub repo, and we intend to expand that with some corpora for other mainstream languages soon. And then if you want to go and find the primary sources for all of those things in green that were on the third slide, they're here. There's a few research directions here. Given that what we've got is a threaded implementation, it's worth asking what would happen if we actually tried running it under Java threads. We did a quick experiment a few years ago and the results were discouraging, but maybe things are better now, and anyway, we've all got graphics processors which can do interesting things too. Okay, I think I've run out of time, haven't I? I better shut up. Thank you very much for your attention.
Let's thank the
3 minutes for questions.
Questions? Can you please walk up to the microphone so that people watching the stream?
I have to warn you, I'm a bit deaf, so you might have to repeat. But anyway.
Quick question, because you
Sure.
mentioned, I think it's a very nice approach that you use some sort of like hash pool to optimize these generalized parsing for context-free grammars, but do you also consider that this idea can apply to like layout-sensitive or indentation-sensitive languages, like Python, Haskell, YAML, whatever, they have indentations and also alignment, whatever, this kind of features.
I'm not sure I heard the question properly. Were you asking me about other languages other than the ones we've been looking at?
Yeah, like
right, okay. You're talking about the offside rule and so on. Yeah, that's not something we're addressing at this stage. I know that plenty of people have had a look at that, but we haven't gone down that road. To be honest, when I'm processing an offside rule language, I run a little preprocessor over it and stick a token in for each indentation value. I realize that that's horrifying to people that love those kinds of languages, but we've been messing with that stuff since Occam. It's not just Python. These ideas have been around for a long time. So we just take a quick fix on it. That's all I have to say at the moment. But thanks for the question.
Thanks.
Any other question? Anyone?
If there's the same part of the algorithm that people are consistently screwing up and forgetting because they don't think they need it, is there an example grammar where that obviously shows up and you just get a very obvious wrong parse if you don't have that in?
Again, I didn't quite catch all of that.
The bit earlier, the part that people keep on leaving out with the
the predictive pops.
Yeah. Is there a reference grammar that if your parser will completely screw up if you don't have the
Very
the
good
code
question.
in there?
It is surprisingly hard to generate an example which will definitely kick that off. Not least of all because it totally depends on the execution ordering, and that tends to depend on the ordering in which things are coming out of these sets, and that of course depends on the hash function that you're using. So what I can say is that if you run the stuff that's in the repo with even some of the small examples, it will report how many contingent pops, as we call them, are occurring. So there are examples you can hone in on. Now, Elizabeth's on her feet, so with a bit of luck, she's got something more useful to say. Okay, I had forgotten that. But you're right, we ought to stick that in as a standard test because, that's the sort of first correctness test. But it is subtle. It's not, we got burned this way ourselves. And the other thing I would say is that the eBNF parser is very easy to write an eBNF recognizer, very easy, it's trivial. But to get the SPPF right, for the eBNF case is very non-trivial. We've published a version, but if I'm honest, there's a big sort of here be dragons sign over it. That's correct, but some of the later variants, which work differently, we haven't done the work to think about what the eBNF SPPF would look like in that case. And I'm not sure that we're in a hurry to do so because it was a stressful time getting that right. Okay,
I
thank you very much.
I think that's it with time. Yeah, let's thank the speaker again.
That's for you, I think. There we go. Sorry.
Right, so the next talk is called Sharing Trees and Contextual Information, Reimagining Forwarding in Attribute Grammars. And Lucas Kramer from the University of Minnesota is going to present. The floor is yours.
Yeah, so welcome everyone. I'm Lucas. I work with Eric Van Wyk on attribute grammars, and I'm going to be presenting some work we did with tree sharing, and the goal of this is to let us write fewer equations and get better performance by sharing and reusing some computations. And as you'll see with some more sophisticated extensions or applications with extensible languages, it's possible to actually suddenly end up with an exponential compiler runtime if you aren't careful, which is something you obviously want to avoid. First a little bit of background about attribute grammars. I'm going to be using a really simple toy imperative language for a working example here. So we can represent languages as context-free grammars and programs as corresponding abstract syntax trees, like this one. Wrong way. So attribute grammars then are a formalism invented by Don Knuth to define the semantics of context-free languages. But they're also actually a really useful paradigm for implementing compilers. In an attribute grammar, we attach synthesized attributes on the syntax, and you can use them to compute information up the tree for different analyses like type checking or collecting a list of error messages. And then we can also have inherited attributes that pass contextual information down the tree, like, for example, an environment that maps names to look up their types. So formally, we can say an attribute grammar consists of a context-free grammar, which has a set of non-terminals, terminals, and productions. There's also a set of attributes, which are synthesized and inherited attributes, which can contain terms or other data structures like an environment. There's a set of occurrences that map what attributes occur on what non-terminals. And there's finally a set of equations that define the values of attributes on productions. So productions in the grammar have a signature. So for example, this if-then-else production here has a condition expression and two statements for the then and else cases. And these signature items are all labeled so that we can use them in writing equations that define the attribute values. So here, the if production, for example, copies the environment down to its children and then collects error messages up the tree. And in constructing the list of error messages, we check that the type of the condition is actually a Boolean. This check is bool function reports an error message if it's not. And we also have this var production for a variable reference. This looks up the name and the environment to compute the type with this check-in scope function, and then also reports an error message if the name isn't defined. So attribute grammars are naturally modular. One can just write down productions in one grammar and then write down additional aspect equations in a different grammar and simply just compose the grammars, and you get a new specification out of that. And so we can use attribute grammars to build extensible languages. We're interested in language extensions that can introduce new syntactic constructs in the form of new productions, and also new semantic analyses, transformations, translations, etc., as new synthesized attributes. And these synthesized attributes can also depend on new sorts of contextual information provided as inherited attributes. For example, consider an extension that introduces for loops to this simple imperative host language. A for loop can be translated into an equivalent while loop. We introduce a temporary variable here to avoid evaluating the upper bound more than once. This should be chosen, whatever name v0 here, not to conflict with anything. Another extension could introduce an ASM attribute on statements to translate into some new sort of assembly code. And we're specifically interested in a model of extensibility where language extensions can be developed independently. So programmers should be able to pick and choose what features they want in their language, just like they pick and choose what libraries they want to use. And this raises a question of how attributes introduced by extension A can be computed on productions introduced by extension B. This is known as the expression problem, a term given by Phil Wadler. We somehow need to define the ASM attribute on for loops, for example, in this situation, where the for loop extension doesn't know about the ASM attribute and vice versa. So the solution that we've come up with to this is that all new extension productions need to define a forward tree on which independently defined attributes can be computed. So this is what the abstract syntax tree for a for loop would look like. A for loop is implemented by this for loop production, and it forwards to a translation containing the loop bounds and the body as children. The actual translation is a big messy tree that I'm eliding here for clarity. The for loop production might define errors directly, checking that the loop bound expressions have the right type. This requires the for loop production to pass down the environments to its children. Other independently defined attributes, like the assembly translation, are computed by default on the translation in the forwards tree, and copied from that tree to the for loop node. This also depends on the environment for those children, which automatically gets copied the other direction as an inherited attribute and flows down through the forwards tree to the children. So this is what the definition of the for loop production would look like in our attribute grammar language, Silver. Here we define a direct equation for errors to give better error messages for when the loop bounds have the wrong type. This also requires one to define equations for the environment, since this is a dependency of errors and type on the children that we need here. And Silver features a modular well-definedness analysis to check that all needed attribute equations are actually supplied. So here, for example, we only need to supply these E and V equations because we are accessing errors on the children, and we know that errors depends on the environment. And then we define the forward to construct the while loop and the counter variable that we saw previously. And Silver distinguishes between terms, which haven't yet been decorated with attribute values, and trees that have been decorated with attributes. So in constructing the forward, we need to convert the decorated child trees back into terms so that we can decorate them again in the forward tree. And this is done by the function new, highlighted here in purple. So now consider what happens if for loops get nested. This is the rough shape of the abstract syntax tree for this code, and I'm leaving out the loop variables and bounds for clarity. So recall the definition of for loop. When we demand errors, this is provided by the explicit errors equation in the for loop production, and this in turn will demand errors from the body in the original abstract syntax tree without using the forward. And then this depends on the equation for body.environment that was applied in the for loop production. Now consider when we have the independent ASM attribute demanded by an independent extension, which doesn't supply an equation for loop. Instead, the assembly translation gets automatically demanded and copied from the forward tree. And this causes the environment to be demanded in the forward tree, and it's automatically copied down from the production that forwarded to it, as you see. And note that we're actually computing the same environment in both places. This is an extra burden on the writer of for loop to have to supply the right environment that corresponds to the one that will be constructed in the forward tree, and they need to supply the correct environment in order to actually get correct error messages. And so we want to share these trees to avoid recomputing the environment. And also, we'd like to define the body's environment through forwarding, just like how synthesized attributes like the assembly translation were defined through forwarding. Also note here that there's potentially 4 different versions of the inner body. In this case, we don't ever actually demand the creation of the 2 middle trees, but we will see an example of that next. So now consider a negation operator that's overloaded for both Boolean not or integer negation. This neg production forwards dispatches to different productions based on the type of the operand. Here, error_expr is just an expression that always reports a certain error message, which is kind of useful if there's nothing valid to forward to. This specification seems innocent enough, but actually we'll see it's quite bad. Because an expression with 3 nested negations gives rise to this structure of potential forward trees. And now considering what happens during type checking, when type gets demanded from this expression, we don't supply an equation for type on neg, so type gets automatically copied from the forwards tree. And it's almost as if we wrote this explicit equation to copy the type from the forwards tree, but this is happening implicitly. And demanding type from forward tree also demands that we construct the forwards tree itself. And to decide what production to forward to, we need to know the type of the operand. And this happens recursively through every version of the tree until we reach the variable x. That should be x instead of 7 there in the expression that was parsed to give this tree. And this has to be looked up from the environment. And this in turn causes the environment to be demanded through every single term in the tree. Since environment is a dependency of type, and the operand's type is used to determine the forward, the well-defined analysis requires that we provide that equation on the neg production. So yeah, we end up computing E and V and type on every possible intermediate forward node. And since the number of potential forward nodes is exponential in the depth of the tree, this leads to a worst-case exponential amount of computation being performed. And this has actually bitten us a few times in practice. For example, we have a language extension to C that adds some Prolog-style logic programming features, which is quite cool. And this works great for small examples, but there's some lurking exponential performance issues that mean it's basically unusable for any real projects we've tried. So a solution to this and these issues is to ensure that there's only ever one version of any child tree that gets decorated, and that we share this child tree between a production and in what it forwards to. So this means that any synthesized attributes demanded by the forwarding for loop production, as well as any demanded by the forwards tree, are computed on the same shared child. And inherited attributes like the environment can now also get passed down through the forward tree. And this sharing can be achieved in their Silver specifications using a new tree sharing operator, which is indicated by the @ sign. For example, @ body in the forwards tree here can be used, it indicates that the body should be used when decorating the forwards tree. Since we statically know that the productions in the forward will all actually supply the environment down the tree, we can actually leave out the environment equations when we're accessing errors in for loop. And we can also apply this approach to the operator overloading example and avoid the exponential blow-up problem. However, we still need to supply an equation for the environment to avoid a cycle. And that's because to compute to the type of n in order to determine how to forward, there'd be a cycle if we relied on whatever production we chose to forward to actually supply the environment to the operand. And also note that both neg and int neg are supplying the environment to the child. This isn't optimal because it requires the writer of neg to give the right equation that matches the one in int neg and bool neg, which in this case is trivial because it just copies the environment, but in practice the required equations can be significantly more complicated for some kinds of analyses. And if neg were an extension production, we wouldn't want the extension writer to have to deeply understand what's going on in all of the host language inherited attribute equations. So oftentimes a hybrid approach can actually avoid needing to write down inherited attribute equations. Instead of directly forwarding to the specialized implementation, we could forward to a let expression that binds the child as a temporary variable and then refer to this variable in the specialized implementation. So this way the operand always ends up under a let expression and that can supply the environment. And this means that the operand is now being shared under the same tree all the time. Yes, so we can pass the environment down through the let expression, through the forwarding, instead of writing the equation in neg. And so the neg production can then always access its type on n, the operand here. So when type or any other synthesized attribute is accessed on neg, we demand it on the let expression and what it forwards to. Sorry, that disappeared. Yeah, and in turn, this flows up through the specialized implementation in the body of the let expression. And more sophisticated language extensions can make this harder because they can actually introduce their own non-terminals. For example, consider a language extension that is useful for expressing complicated Boolean logic expressions. In a condition table, this expression here, consists of a series of Boolean expressions, each with an associated set of truth flags. The table expression is true only if the true or false or don't care truth flags, which is indicated by the star there, in at least one column match the truth values of each row expression. So for example, if the first two rows were false, I less than j and x equal y were both false, and the third row is true, not b, the table expression would then be true because these truth values match the second column of truth flags. And a condition table then forwards into a sequence of let expressions that bind each of these row expressions, and then this is followed by a Boolean expression, which happens to be in a disjunctive normal form, that implements the truth flags. And actually note that this expression on the bottom right, this effectively mirrors the transpose of the truth flags in this column structure here. So this is what the abstract syntax tree for a condition table expression would look like. So we have a chain of cons row productions, which each have truth flags and a condition expression. And note the children are drawn in the wrong order here, from where they actually appear left to right lexically. This will help make things clearer in a second. So this is the structure of the let expression chain that makes up the forwards tree. And we'd like to share the row expression between both versions of the trees. So host language inherited attributes, like the environment, can then flow down over the forwards tree, and we can avoid the extension syntax needing to supply a host language inherited attributes to the embedded host non-terminals, the expressions in this table expression. And the extension syntax can still make use of those inherited attributes that are supplied through forwarding. For example, we can define errors on the table rows to better provide error messages for a condition table, checking, for example, that there's always the same number of truth flags in each row, and also that the row expressions actually have the right type. And this demands that the errors and type from the row expressions, which depend on the environment that was supplied through the forwards tree, actually are there. And also any independently defined synthesized attributes, like ASM to define the assembly translation, we can just simply compute that on the forward tree like normal. And the challenge now is how do we actually construct a forwards tree with this pattern of sharing? Since the row expressions aren't direct children of the condition table production that's forwarding to this translation, we somehow need a way to share trees that were decorated in one production and use them in the forward of another production. So these are the signatures of the productions that represent a condition table. The sequence of rows that make up the body of the table are represented by this T rows non-terminal. And the condition table production constructs the Boolean expression that should go at the end of the chain of let expressions. And this gets passed down the table rows using this higher order inherited attribute called cond. And this expression that we construct only refers to variable names and doesn't contain any trees that should actually be shared. And then the forward of cond table is computed using the trans attribute. This term does contain some shared trees. So if trans were an ordinary higher order attribute, this would force us to undecorate the expression and then redecorate it when the forwards tree is decorated. Instead, trans is a new sort of attribute we call a translation attribute. This is a variant of synthesized higher order attributes for the specific purpose of constructing shared forward trees. The equations that are specified for a translation attribute construct terms, just like an ordinary higher order attribute, as we can see in the nil row production. However, unlike higher order attributes, we permit sharing in a translation attribute equation, which we can see here in the cons row. And also the value of a translation attribute is a decorated tree, and we can share it just like we would share a child, as we see in the cons row and also in the con table production where we forward to the shared value of the shared tree constructed by rows.trans. So while some extension inherited attributes are explicitly defined on the extension syntax, by default, other attributes like the environment flow down through the tree that we built with the translation attribute. Thus, the environment and others don't need to be supplied on trees with the translation attribute. There's also some cases where sharing isn't feasible or isn't the right choice. For example, consider the ABC halide extension. And this is another language extension to C that we developed, which is inspired by the halide framework for image processing. Here, the programmer can write some nested for loops, along with a schedule of transformations that should be applied to the loops. For example, here, we split the outer loop into 2 nested loops with these 2 loop variables, and then unroll one of the resulting loops to generate this code on the right. And the specified loops on the left, we need to decorate this syntax with some attributes, like the environment, to compute this translation. And also note the same loop body appears in the translation, but it isn't possible to share the tree here because this requires duplicating the body. And doing that would be problematic because it isn't clear which location in the shared tree should actually be supplying the environment. And there's also some additional issues I won't get into that prevent us from using translation attributes here. However, it's not actually a problem in this case that we can't share the trees, because like the for loop extension we saw at the beginning, this doesn't really suffer from the exponential blowup issue that we saw with the overloading example. However, even so, constructs like this aren't typically nested. And the main point here is the extension developer has the choice of whether to share trees or to not share them as appropriate, and using the @ sharing operator or the new function lets the extension developer make that choice. So for evaluating this, we considered 10 existing language extensions to C. And previously we had a really brittle hack for trying to avoid some of these blow-up issues, but this was incompatible with extension inherited attributes on host language and on terminals, so it limited extensibility and had a number of other issues. So out of 74 places in these extensions where we used this hack, 39 of them could be replaced by tree sharing, avoiding writing inherited equations like with for loop. 5 of them could be shared, but involve dispatching, like with neg, where we still needed to supply inherited attributes explicitly. 15 of them we could do tree sharing using translation attributes and avoid supplying inherited equations, like with cont table, for a total of 59. And there were 15 that shouldn't have really been using sharing in the first place, extensions like the halide extension here. The main point is all potential performance issues due to redecoration were addressed due to sharing, or addressed using sharing. And also note, in one typical example extension here, we saved 36 out of 900 lines of specification of inherited attribute equations. We didn't actually finish updating all the existing extensions yet, but this is a fairly typical example. So some modest simplifications too. We do have some future work remaining. Previously in Silver, one could just refer to the name of a child or a local to refer to the undecorated tree, and the Silver compiler would insert a call to new explicitly. This convenience feature was really kind of a mistake because this means in a lot of places where you probably intended to share the tree, it would just get implicitly decorated twice, and this would happen silently, so there's nothing to really alert the specification writer that you should maybe be using sharing here. Another thing we found is that when inherited attributes are supplied through forwarding, we often end up with circularities that are actually okay in practice because of laziness. For example, in the let binding version of neg, this works out to be okay, where we have forward depends on the operand type, which depends on the operand's environment, which depends on the forwards tree, essentially. But this actually isn't a problem. But there are some existing circularity analyses, like the one Knuth developed in his original paper and some others that have been extended for higher order attributes, which would actually flag this as a false positive, because if we tried to adapt it for tree sharing. There are some cases where we actually do have harmful cycles that are created, which we need to break the cycle by supplying an explicit inherited equation, but we'd really like a more precise analysis that would tell us when we potentially have a harmful cycle. And another area of work is in supporting, another area of work is to support dispatching to arbitrary extension reductions. For example, here we have this neg reduction that instead of forwarding to a case expression, we want to supply explicitly, or we want to dispatch based on the type to some extension reduction potentially. And that is, that leads to more flexibility, but there's currently some issues that prevent us from actually writing the specification where the modular well-defined analysis actually would disallow this n.env equals e.env equation. And we'd really like to also not have to write an equation for the environment and what this forwards to, because we know that it's always going to be supplied before forwarding. So in conclusion, we revisited our approach to how contextual information is handled in forwarding. We provide a more principled way to share trees and avoid recomputation of analyses. We expanded our well-defined analysis to ensure there's no missing equations with sharing. And we demonstrated this works and is useful in AbleC extensions. And overall, we're giving extension developers the power to decide when it is appropriate to share trees and giving them the tools to do so. So with that, I want to thank the reviewers for their helpful comments and feedback, and I'm open to questions if there's any.
Let's thank this speaker. Questions? Can you please walk to?
Thank you very much for your presentation. I was a little bit surprised when you brought up the translation attributes and made this comparison with higher order attributes, because I was under the impression that with the forwarding mechanism, you in some sense already generalize higher order attributes by deciding when to make copies or when to apply sharing. So could you reflect perhaps a little bit on precisely the relation between translation attributes and forwarding and higher order attributes?
Sure. So forwarding is defining the translation for a specific production, sort of the entire abstract syntax tree that it constructs. The problem that we're facing with this condition tables extension and a lot of other more sophisticated ones is if you have a whole another non-terminal or some extension language that you need to compute a translation of it and have some root production that's going to forward to that translation, you somehow need a way to build up that tree you're going to forward to and include the shared subtrees within that. Is that clarify?
Yeah, so maybe a more specific follow-up question is whether this combinatorial explosion problem that you mentioned is something that would occur if you were to use just purely functional higher order attributes.
Sorry, can you speak up a little bit? It's kind of hard to hear.
So perhaps, so if you were to use just purely functional higher order attributes, would this combinatorial explosion problem also come up?
Oh, instead of forwarding using higher order attributes? So no, so that is another alternate way of doing extensible languages is instead of having productions individually forward, you have a higher order attribute over the entire abstract syntax tree that does a lowering pass that eliminates some productions. Yeah, that's another way of expressing it that sort of allows different sorts of extensions. You can add, you have to make a trade-off between having some restrictions on what new productions extensions can add, or versus having some restrictions on what kinds of analyses an extension can add. And this is kind of a, forwarding, it lets you add arbitrary new attributes. And doing that kind of translation, you can't define an inherited, or you can't define an extension analysis necessarily on through forwarding in that approach. Sure.
Yeah, another question.
Yeah.
Thank you for your talk. So I was wondering, when you put in this share annotation, do you get the exact same semantics for all the attributes? Will they have the exact same values as without the share?
So without sharing, you're creating two versions of the tree, and hopefully you got it right and supplied the right inherited attributes to the first version. But it's possible too that the extension writer could supply some environment in the extension reduction and then ends up getting a totally different environment in what it forwarded to. So with sharing, yeah, the goal is to only supply one version of the context.
But if you gave the same inherited attributes to all of them, the semantics would be the same, or?
Yes, if you supplied if you wrote the right equations before using sharing, then now using sharing, there should be no difference.
So could you automatically detect in that case that you could put the sharing there, or?
That's not really possible to do modular in a modular way if you don't know about all possible inherited attributes, because you can have another language extension that's adding an additional inherited attribute, and if you aren't using sharing, it might decide to supply one value before in forwarding and a different value in whatever tree you forwarded to.
Okay, but you could have a global analysis that could hint at, okay, you could put sharing here and you would get better performance, or?
You could do, in theory, you could have a global analysis if you didn't care about modularity in the way we do. I think in practice, there's probably reasons that it would be something you'd want to make an explicit opt-in, I think. Yeah, you could very easily end up not sharing something that you'd expect would be shared if it was implicit, and you really want the programmer to know if they're intending something to be identical, having the identical context or not, just for helping develop extensions. Yeah,
right, let's thank the speaker again.
And then I just mouse over the current slide? Yep. Okay, cool. Sweet.
Right, so our next talk is also on attribute grammars, and it's called NanoPass Attribute Grammars, and Nathan Ringo, also from the University of Minnesota, is going to talk about it. Floor is yours.
Yeah, hi. I'll be talking to you about NanoPass attribute grammars. This is joint work with Lucas and Eric. And yeah, there are these two approaches that exist in the literature, NanoPass compilers and attribute grammars. In NanoPass compilers, you're trying to design a compiler as the composition of a lot of tiny, simple passes. In attribute grammars, on the other hand, you've got your one big syntax tree, and you've got a bunch of attributes decorating it, and you use these to perform analyses. NanoPass compilers have a couple wins to them. You can sort of rely on your one big correctness property of semantics were preserved. On each of your passes, if each of your passes is semantics preserving, the composition of them should be as well. So you can test them by saying, hey, was this actually semantics preserving for some particular input? And you can reason about their correctness in those terms. And since these passes are tiny, isolated little things, this is actually pretty easy reasoning to do informally. On attribute grammars, on the other hand, you sort of have like this a frontier of correctness, where you have to try and figure out what does it mean for this attribute to be correct in the context of this whole AST. So it's still obviously very possible to reason about the correctness without too much difficulty, but it can be a bit trickier than just having this one property that you're always thinking about. On the other hand, attribute grammars are a lot better when you want to check properties of the compiler itself statically. We have analyses for checking that it's well-defined, non-circular, all these things, and they work great. They're also great for talking about complicated data flow, analyses that do need to walk the whole tree, collect up information, do fun things with sets. Great fun, easy to write in attribute grammars, not so much with existing NanoPass compilers. So the goal of this work is to get the best of both worlds. Check all of these green. So first, I'll go over a bit more background about NanoPass compilers. In the NanoPass approach, as I said, you're splitting the compiler into these tiny passes, nanopasses in reference to their size, between slightly different languages, in that you might define a variant of a language. A lot of these passes, 80% of them roughly, are are going to be things that are just like lowering or simplifying or normalizing the program. Say you're working with an imperative language that has both if-then and if-then-else. You might want to normalize away the if-thens because you can just put an if-then-else with nothing as the else case. You also might want to normalize things like if you have a polymorphic add production, you might want to change that to be integer addition once you know that the types are integers. This will make other passes later on easier to write because you can just dispatch on the production, like in an attribute grammar way, without having to think about, hey, I need to check the types. And generally, yeah, this will just make later passes easier. For the other passes that you'll have, they'll generally be doing like kind of classical compiler things like optimizations, type checking, these sorts of things. Here, your passes aren't necessarily going to be super small anymore, but in the input should be pretty tightly constrained, thanks to all the lowering you've been doing. And you can still reason about them with your one big property of, is the semantics preserving? Yeah, that's that. And this was originally introduced as a scheme library at ICFP 2004. And this is used in the Shea scheme compiler. And as far as I know, they're very happy with it. So just to make this more concrete, I'll sketch out an example compiler, or an example of some passes for a compiler for an imperative programming language. The first thing we might do, say, is get rid of if-then, as mentioned before. So we'll define a new language. We've got L0, which is like our initial source language. And we might define a new language, L1, which is exactly the same thing, but without the if-then production. We'll then have a pass that goes from L0 to L1, transforming according to that rewrite rule. We might then define the next language, L2, where the difference between L1 and L2 is that types are fully explicit in L2. Every expression has a type attached to it. And we could, again, have a pass there that does that. We could then have a language L3 in which all the polymorphic operators have been transformed into monomorphic ones. So where before you had a polymorphic addition production, afterwards you'll have int add, float add, complex add, whatever other addition productions you might have. Maybe then you're going to get rid of complex numbers because your language has records and your backend can deal with those. You don't want to have to deal with complex numbers. So you could lower those in another pass. And L4 would again be like L3 with some stuff removed. You keep on having a bunch of passes like this, of this nature. And eventually you'll get to the end where the last thing to do is you can flatten your expressions. You can take expressions that have other expressions as their children and say, I'm going to make a new atomic expression that has integers, variable names, may float literals, nothing else, and translate down to there. And then at the end of your chain of languages, you'll have a language that's trivial to translate to assembly. Now I'll have some background on attribute grammars. You'll see if you saw the previous talk, we can't just share trees, we can share slides too. So yeah, attribute grammars, you represent the structure of the object language program as a tree. You then have attributes you're putting on it. Synthesized attributes are going bottom up. Inherited attributes are going top down. And yeah, formally, it's context-free grammar. You put on synthesized and inherited attributes. You have a relation for where they occur. And you have some equations. Attribute grammars as we know and love them. So we can define some criteria that a nanopass attribute grammar formalism should have in order to merge these two different bodies of work. First off, we need to easily be able to identify the syntax of many different languages. It shouldn't take much more effort than saying L1 is L0 without the if-then production. We certainly shouldn't have to re-specify the entire language. The nanopass formalism, this is a large part of the point. This is super easy to do there, well supported. Emulating this in attribute grammars is annoying. You're gonna have to list out all of your non-terminals again, and then copy all your productions over. If you need equations, write those again. So enough boilerplate that you just don't do this. The second criterion would then be checking that whenever you're building a tree, you're actually building it in the language you expect it to be in. So if you're in the output of some transformation, and it should be, for example, removing if-thens, you better not be adding any new if-thens. And this applies later on too. If you're way after that and the language just if-thens are completely unrelated, you better not be producing any. This also applies to analyses that you want to do on the tree. If you're computing types and complex numbers aren't supposed to be there, or getting the results of type checking and complex numbers aren't supposed to be there, you better not be there. The nanopass framework kind of does this. It checks types at the boundaries. Like at the boundaries of a pass, it will check to say this tree doesn't contain this thing I'm expecting it not to. But within a pass, there's nothing checking that your intermediate results are going to be in the language you expect. And in attribute grammar, since we don't really have a way of talking about these sublanguages conveniently, nothing really there. Our third criterion would then be that we can specify these transformations pretty easily. For the large chunk of them that are like pretty much trivial rewrite rules, we should be able to just write them down with about that level of complexity. This shouldn't take half a page, it should take 3 lines. For either one of the if-then or making addition not be polymorphic. We especially shouldn't have to write things saying like, oh, how am I going to handle while loops? Well, the transformation should just be applied recursively. It should just work. The nanopass framework and the nanopass approach make this pretty easy. Implicitly, you get the clauses that you left out saying, propagate this thing recursively. And attribute grammars, there are a lot of extensions that add this approach. They're not built into the formalism, but yeah, they more or less work. So we need to make sure that we preserve this. Our fourth criterion is that when you're describing your semantic analyses and implementing them on a language, you should only have to write them for the things that are in that language. For example, once we've removed if-then from the language and we're doing type checking, we shouldn't have to care about if-then or think about it ever again. We also want this to be checked statically. We'd still like to keep the nice things from attribute grammars where we know you're not missing any equations, and know that at compile time without realizing, hey, I forgot a case, and getting a compiler crash. The nanopass framework doesn't really have a nice mechanism for doing semantic analyses. Like you can always just bail out and call scheme code, but the scheme code there isn't going to check and like statically tell you, hey, you forgot a case. And attribute grammars, like missing languages again, kind of hurts you here. If you're trying to avoid defining n copies of your entire grammar for your n different languages, you're going to have a bunch of missing equations. Like if you're trying to share the same if-then, like if-then is going to still have an attribute occurrence for something like typing that came from statements. So it's going to yell at you, oh, you need an equation here. You can make that equation just crash to tell the analysis to go away, but then you've kind of lost the point of the analysis. What if you did actually need it? So yeah, they don't really get to check that box either. Lastly, we want to keep the results of analyses across sequential tasks. This should actually be a check for nanopass. But if we have like a type attribute we computed during type checking, we want to be able to like save this and move this across passes pretty easily, even as we're like rewriting the whole tree to get new trees. In the nanopass framework, it's reasonably syntactically convenient to just add this as a new child and say, after this point, I've got a new child, and that's my type. It's a bit of boilerplate, but it's very manageable. Versus in attribute grammars, there isn't a great way to do this. Like if you're in the normal approach where you've just got one tree and you're doing a bunch of computations over the tree, the attribute's demanded when it's needed, and you don't really need to think about persisting it. But once you start building new trees, nothing's copying that attribute over, so you don't get to keep it by default. So we have a formalism that we think satisfies these criteria, our nanopass attribute grammars. We've got 3 main parts to them. We've got our collection of language elements, which we call E. We've got a family of languages, L, and a composition of passes, C. So the family of language elements is basically a huge, not necessarily well-defined attribute grammar, with every non-terminal that we ever use in all of our languages, every production that we use in all of our languages, all the equations, everything, all in just one big kind of soup. So it's not going to be well-defined because you're going to be missing equations like how do I type check an if-then. However, you can type check this actual specification. I'm going to go over the rules in a bit of detail because there's going to be another type checking looking analysis later. So here we're looking at what it looks like to type check a production call, like a call to a production P with 2 children, T1 and T2. We've got 2 judgments here. The first one says, given the context of our whole specification and the production we're in an equation for, does some expression E have type tau? The second one says, given that same context, so we're in some production's body and we've got the whole rest of the specification as context, is this equation well typed, x dot A equals E? So an example rule for this to check to see if a synthesized equation is well typed goes something like this. You're trying to check the equation at the bottom, so you look up what's the type of the production, you get the signature here, you say, hey, X, the name of the left-hand side, matches, okay, cool, and A is a synthesized attribute, it's in our set of synthesized attributes. Cool, this applies. You then check that the A attribute actually occurs on the non-terminal, X, and then that the expression has the right type, whatever type we're looking up from E, the context mapping attribute names to their types. And yeah, assuming that all works, it should be type correct. Importantly, anything we're doing on E, we only do once across the whole compiler because it's not split into sublanguages. So when we're doing type checking, we're only doing it once. There's also another thing we have in E, which is not traditional necessarily in attribute grammar systems. We have a notion of annotations. These are, I believe, also known as, sorry, not implicit attributes, inherent attributes, I think, in other systems. But when you construct the tree, you can provide values to it for that occupy the same namespace as attributes. Sort of in a sense, a synthesized attribute gives the attribute value from the node itself, and inherited attribute gives it a value from its parent. An annotation lets you give it a value from whoever built the tree, who's not necessarily its parent, especially when you're talking about these transformations. So here we have like an add of the integer 40 and the integer 20, and we're explicitly passing int tie as the type for the annotation. So if an equation depends on e.type, where E is this tree, it'll get int tie, as long as there's like, because no equations will be there, they'll be asked for what its type would be. These will come in handy later. These are, yeah, these are just in E. So in our collection of language elements L, we've got languages like the L0, L1, et cetera from before. They're pretty much just subsets of E. You've got some productions, non-terminals, attributes, equations from E, and some of the attributes are marked to be annotations. So within an individual language, an attribute is either a normal attribute or it's an annotation. So it'll always just be pre-computed and sitting there. Within each language, you should have a well-defined attribute grammar. So you can still use existing well-definedness checks from the literature there. And yeah, you'll have to run it once for each language, but this is pretty much acceptable. They're fast. So we need a way to specify these things. The first way that you'll probably do at the very start of your compiler is to actually list out everything that's in it. So in the syntax of our prototype system, this is how you'd list like the start of an imperative language. You'll say, hey, I've got statements, that's non-terminal, they've got some productions, you list them out. Any non-terminals that you list, or any productions you list that are non-terminal will get included, and any attributes that are present and not annotations will become part of the language as well. So this, of course, would go on pretty long. Like this would be your whole language, whole source language that you intend to process. Then there's the second way that actually provides like the convenience of being able to extend languages. You can say, I'm defining a language L1 that extends L0 by removing the if-then production. I might then say new attributes are present that weren't present in L0. Like now I can compute typing. I might have an environment. I'll have other attributes. Everything I need to do type checking. I could then have another language, L2. These are the same ones from the example before, where after L2, we're doing type checking as we move from L1 to L2. So in L2, we annotate expressions with types. So the type should already be computed by the time we're in L2, and it'll just be sitting there ready for use. So here when we extend, all we do is we add type to the set of annotations on expressions. We could then have another language, L3 extending L2, where we get rid of addition as a production, but instead we've added in our complex integer and floating point addition productions, which yeah, may make other tasks easier. So once we have our languages and the rest of our attribute grammar parts ready, we can then define transform attributes. Transform attributes are how we map one language to another. So you'll write some, like for the removing if-then, you'll have an equation on the if-then production saying that the result of removing if-then is that if-then else there. You can like just demand the attribute on your children to get it recursively applied, and then you'll build a new tree and return the tree. The benefit of using transform attributes over a normal higher order attribute is that they're going to generate equations for you. On all of the other statements and all the other productions across all the non-terminals in L0, you're going to get an equation automatically generated that propagates the transformation recursively downwards. So this is all you need to write for the pass that's going L0 to L1. And the rest is generated for you. Similarly, to go from L1 to L2, you only have to write that one line. The type attribute is computable on L1, so when it's present as an annotation in L2, we just compute it and put it in the trees. And all those equations are automatically generated, so you've got one line of code for that whole pass. You can have more complicated equations too. When we're going from L2 to L3, removing the polymorphic add and having specialized ones, we can have a whole expression here that's looking at the type annotation, doing branching on it, doing all these things, producing new trees. And we can analyze it and know we're always producing a tree that is in L3. And anything we're doing on type is valid for type being in L2. And type will get moved to L3 as well, because types will get a generated equation saying, here's how you map a type from L2 to L3. Because type doesn't actually change, that's actually a no-op, but if it did, you'd be able to apply it there in the annotation as well. So, like, to do this whole check, we have this idea of language correctness. In the same sense that we have like a type correct program, we have a language correct program. In the same sense we have a type checker, we have a language checker. This ensures that any trees that we build or accept are in the language we expect them to be in. When we have a transform attribute, it's always operating on, like, you have a fixed source and target language for it, so it should be producing trees that are in the target language from ones that are in the source language. Higher order attributes are going to be in the source language generally. You're using them for optimization. If you're using them to, do analyses for the purposes of making optimizations, generally you're going to be doing these analyses within the source language, so this makes sense as a default. There is some subtlety here to make sure that when you're doing an analysis, anything that you're computing isn't going to have something weird showing up you expect it to be gone. For example, complex numbers. If you're doing some analysis that was written before complex numbers were removed, it might not pass a language check afterwards. Probably you want to save it as an annotation and then it'll get mapped properly, but possibly it might just be wrong. Either way, the language correctness check will flag it. So here we can look at the top level rules for it, a couple of the top level rules. We have a pair of judgments again. The first one saying that in the source language L, and given our same context, some expression is language okay. In the same way something would be like type okay, it would pass the type checker. It's language okay, it passes the language checker. Then we also have a judgment saying that some expression E is in a target language, given context and a source language. So the difference between the source and target language being different is, important for keeping track of them. In the case of inherited and synthesized equations, where the attribute is inside our set of inherited or synthesized attributes for the language, we are just propagating the check downwards to the expressions with the same source and target language, L for both, when we're checking against the equation within a certain source language. Contrastingly, inside a transform equation, when it's inside the set of transform attributes, we're actually going to look up what is the source language, what is the target language of that transform attribute, and when we propagate it down, we're going to check they match. We're also checking to make sure that the source language of the transform attribute actually matches the one that the attribute is put inside, but the prototype system always ensures that's the case. We'll then have language checking rules like this. This one's checking that when you call a production constructor, it's actually building the production that's in the right language. So when you call the production constructor P prime, it checks that P prime is in the set of productions for your target language. Then it looks up the signature, says, okay, it's going to produce an X. And then it should, there's something that the X was used for, that this is a simplified rule from the full rule that's in the paper. Ignore the X. Then we check for each of the children that they're valid in the target language, L sub T as well. So if all the children are valid in the target language and the production is actually in the target language as well, we should have a tree that's in the target language. None of these rules are that complicated. They mostly do just look like we're propagating down, check that this is in the target language until you hit a call to an attribute, and then we check what a language should this attribute be producing. They're pretty straightforward. The analysis is almost a top-down pass. It's pretty easy, pretty fast. For the final part of the nanopass attribute grammar formalism, we've got compositions. Here you pretty much string a bunch of transform attributes together and say the compiler is the composition of these in like a normal function composition-y way. The source and target languages have to match up, of course. But yeah, it's simple, easy, it's composition, and we get nice compositional properties. So we at least need one to just talk about what are the semantics of this program, but it actually can be useful to have several of these. For example, you might, like testing is one of these big advantages, you might only want to run a couple passes of the compiler for testing purposes. If you've got some optimization passes, you might also feel like twiddling them to see different things. Or if you're trying to write a compiler like GCC that has multiple different source languages, you could do that too. You could share, for example, languages 10 and on between multiple different front ends that all eventually translate to that shared language. So in future work, we'd like to allow attributes to explicitly identify their language. Right now, you just get those two simple rules of transform attributes always have a fixed source and target, and synthesized and inherited higher order attributes are always in the source language. There are cases where you might actually want to say, this isn't always in the source language, it's always in L3 in particular, or L7 in particular. In some sense, attributes are implicitly polymorphic, and we'd like to give the user the power to say, we don't want that polymorphism. We'd also like to implement this in a proper, like full-featured attribute grammar system. We have a very rough prototype right now, like to prove that there's no sudden and hidden gotchas with the analysis pretty much, and a sketch of a Go compiler in that. But it'd be nice to have this in a proper thing so we can try out writing a C++ compiler. Maybe this would be in Silver, and maybe this would just be a new prototype system. Yeah. So in this work, we've extended attribute grammars to allow concisely specifying a bunch of different languages, transformations between them, and then allowing for the analysis of completeness, type correctness, and this new language correctness property. We'd like to thank the anonymous reviewers for their helpful comments on improving the paper, and I'd like to thank all of you for your attention. Do you have any questions?
Right, let's thank the speaker. Questions? Yeah, could you please walk to?
So thanks for the talk. I think it's a very interesting framework that you can use to develop a compiler and also address the expression problem to some extent, because we know that we have different data types and different attributes in different phases, so they can express this in this language. So I'm wondering, do you allow that the user can like inject arbitrary code in the attribute grammar so that we can, do really, really complicated things in real world compilers? Like even you want to resolve the name of a method, you may even, let's say, open some library binary file, and you have to decode like the signature of that method so that you can do type checking. And this, I don't think you can easily, have some domain-specific language to do that, but rather a general-purpose programming language.
I mean, anything extending like what sorts of analyses you can do in an attribute grammar should apply pretty cleanly here. Like if you have some way to, if you need to jump outside of the formalism to do some low-level parsing packed binary data or whatever, that should just work if you put that in an equation, because synthesized and inherited attributes are computed exactly as before, and transform attributes are computed like higher order attributes are. Does that address your question?
I think my question is, if you can inject arbitrary code, I think this problem should be solvable.
Like into the compiler?
Yeah, in the grammar maybe. In a language definition, let's say, you can inject some code, some actions.
In an earlier version of this idea, we had a notion of like open and closed languages, which kind of mirrors Silver has a notion of open and closed non-terminals, where you say that, oh, well, maybe there's some unknown to me currently productions that might end up inside this language later. It ends up being tricky and subtle. I think right now our position is essentially that forwarding, if you want to have an extensible front end, forwarding is the right way to go there. And you might forward your way between L0 and L1. And then once you're in L1, then it might make sense to do all your nanopass stuff to do the middle end and back end of the compiler.
Okay, yeah, I think we can talk more during the break.
Okay.
Thank you.
Any other? Yeah.
Well, thank you for your great talk. I suffer a lot with using high-order attribute grammars, and I miss some of features you present today. But sorry, I wrote several grammars where I did a lot, there was a lot of computations, attribute computations, that before we could rewrite the source into the target language. The slides you show you were more kind of a syntactic evolution of the language. Can you do that mapping dependent on attributes?
Yeah, that's where annotations come in. So if we look at like this one, for instance, in L2, we're expecting to have the types as annotations. So the computation's already been done and we stored it there. We're just storing it so that it's easy, so we don't have to recompute it after rewriting. But you can then dispatch based on the type. You can use it as an annotation. If there were more attributes present on L2, you could use them too.
Thanks.
Yep, go ahead.
So in one of your opening slides, you mentioned that attribute grammars are popular because of it's easy to reason about the data flow. So could you reflect on to which extent that is still possible for your framework? Like how easy is it to understand how information propagates from one language to another? And for example, can you make like nice diagrams or visualizations of this?
I don't have anything currently that makes nice, pretty pictures, but I mean, conceptually, it's not difficult. A nice property is that between like your languages, like when you finished going from L1 to L2, the tree there should be like a genuine tree without any like secret dependencies backwards. If you want to like print that out or make a GraphViz chart of it, should be no problems with doing so.
Right, let's thank the speaker once again, and Ron wants to make an announcement.
So an announcement concerning the dinner tonight. We have some news. Quickly share my slides. So we are 37 participants from the two events joining the dinner tonight, and this is the restaurant. Well, if I can share my screen. No. Okay, it's already there. Sorry, displays mirror. Okay, so it will be tonight, of course, at the restaurant Uviriato. So this is the address, okay? We will meet here in the lobby at 6:30 or at the restaurant at 7:15, okay? If you go direct to the restaurant, just take a picture or write down the address. It's very easy to get there. We can choose, we are a big group, so we have to choose from 3 alternatives, so meat, fish, or vegetarian. So the good news is that the price includes wine. The bad news is that tomorrow we start at 9. Okay, so, yep. And so this is how we get there. So it's the city center of Cascais, so I don't know, it's 20 minutes walking from here, from the hotel, okay? So, see you after the break, and later tonight in the restaurant, or in the lobby, thanks.
Do we need to decide if we fish and meat in advance?
No, we can choose at the restaurant, okay? Yeah.
Oh, you've got to mix it, I see. And is the mic up there on? Because it was off at the beginning. Can I just go and test it for you? Okay. Yeah, that's good.
Yeah, you try to find a counter. So if you cannot find, yes, you can have some reliability. Because what we are doing is actually a boundary approach. Because you know that the general problems are solved. But fortunately, the boundary approach is decided so that we can figure out some sort of SMT encoding to this problem. And we also prove that this is sound ambiguous so that we can have this kind of solver. And this solver tells you, yes, your grammar is ambiguous. It's the sentences up to this point.
I'm sharing that session.
Oh, sorry, I should have introduced myself. Completely missed it.
Which one are you? Oh, you're the third
I'm the
one,
last one, yes.
Okay. The dreaded ChatGPT, okay. So
GPT-3.
I was wondering how long it was going to be before something popped up. So this isn't modelling specific, though, is it? This is.
When you say modelling, do you mean more formal modelling or models as in language models?
Neither. I mean, the first two papers are on models, as in modelling as a software engineering concept, not large language modelling. It's okay. I'll mention that we've got two modelling papers and then a large language model, which has nothing to do with that kind of model.
No, it's not. It's not. Yeah.
Yes, but it's not about what class of grammar? Yeah. So the grammar we are considering is, I think in this paper we only conduct experiments on layout synthesis. Some fragment of Python, Haskell, YAML, SAS, grammars they have these indentation rules, offside rules, alignment. So these kind of features. Yeah, it's still very, very hard.
So you have like essentially extra terminals for trying to entering and leaving SK levels, but the grammar backing out still LAOR.
Not for Haskell. Haskell is awful. No, Haskell is evil. For Python, there is a way to make it conditional. Yes. There is a way for Python to make it. For Haskell, I think, in general, and also for other more complex combinations of these layout features, it's really hard to figure out whether it is conditional. Because this problem is also conditional. Judge if a conditional language is actually conditional. And even, if I remember correctly, even not judge if a conditional grammar is regular. Right? Yeah, this is also hard. So many uncycle problems.
I'm pretty sure it's possible it's decidable if CFG is regular because you can, there's some pattern.
Yeah, I mean, there's some pattern, but they are just ad hoc stuff. I mean, I'm talking about like a general problem deciding if CFG is regular. Yeah, and that one, if I remember correctly, is on this. So I think we can find this result in some papers or even some textbooks. Yeah, that's true. So you see there's something and layout is even harder. That's why we can use things. There are very few margins kind of area, but they are still very like important problems when you review. And also not just layout synthesis, because I also know there is some concept of data dependency grammars. So let's say they can have some constraints over the non-terminal symbols in your grammar. And in that case, yes. But I think topology is more or less general to that because we can, there is a way to encode them just as a first order logic optimization for a condition, and then you can still, once you know how to encode that, you can still be So yeah, I think that's
So I guess in the way the first session is talking, those taking the session is talking about like the difference between like you might have a persistent grammar being compiled, or you might be interpreting it in like the GLL. Is this kind of just as well as executing it?
I think for GLL, it doesn't really care about ambiguity because that is a type of algorithm which produces
Okay, okay. Thank you for reminding.
Yeah, I mean, robot yourself.
How to connect with this?
So there's a cable. Where's it gone? That's it.
Yeah, it works for me. How do you... I can see it on this screen, but okay.
I had it up there, sort of random pictures of the countryside appearing down there.
Okay. Okay. I don't need this screen.
Okay,
Yeah.
just a test.
Do you have any other connection?
No, can I
okay,
set up?
Yeah. Ah, okay. Okay, it works. Yeah. Thank you. Thank you.
Could we just do another AV
Yeah,
check?
yeah.
That's
Okay.
I'm sure it'll be fine. But, my machine wasn't, so I'm
Oh yeah, yes, sir. Let me check something now that I'm here already. Hello. Hello? Yeah, it's working. Very good.
Good afternoon, everybody. Welcome to the last session of the first day of SLE. I'm Adrian Johnstone, in case any of you have forgotten in the last 2 hours. This last session involves models of two kinds. The first two papers are about modeling the software engineering discipline, and the third paper is about large language models, which is completely different, but somehow they've all ended up in a session on modeling. Our first speaker is Wei-Xing Zhang, and you're ready to go. The floor is yours.
Okay, thank you. Good afternoon, everyone. My name is Wei-Xing Zhang. I'm a PhD student from the University of Gothenburg and the Chalmers University of Technology. And I'm also very happy to introduce my co-authors, Regina Hebig, who is a professor from the University of Rostock in Germany, and Daniel works in the same university as me, and he is my PhD supervisor. And Jan Philipp was also a professor in University of Gothenburg, and now he is working for Citaso in Germany. Our paper is about automated extraction of grammar optimization Lua configurations for metamodal grammar co-evolution. There are two directions of co-evolution. We can migrate metamodals according to the changes to the grammar, and we can also migrate the grammar because of the changes to the metamodel. And here, our paper is about migrate the grammar when the metamodel changes. Let's take a look at these two pictures. These are two programs expressing the same contents, but they look very different. Why is that? Because they are conforming to different grammar. The left one conforms to the grammar which is generated from the metamodel. And the right one conforms to the grammar created by an expert, even though the two grammar adhere to the same abstract syntax, but the programs of these two grammar still look so different. And the left one was what we got in a project. But why did we generate grammar from metamodel? The story of the project was years ago that we wanted to explore blended modeling technology in that project. And as a start, we developed a textual language for EtherADL. EtherADL is a metamodel-based DSL, which used and it is architecture description language which used in automotive embedded system domain. And because it is a metamodel-based language, and the metamodel is already there, so we can generate the grammar from it instead of designing grammar from scratch. And such a metamodel-driven way is also very suited for blended modeling. And by the way, what is blended modeling? Here is a scratch map for that. For example, in a language, there are multiple concrete syntax. They are conformed to the same one abstract syntax, and they interact with each other seamlessly. And it is allowed to have some inconsistencies between the concrete syntax. And then let's go back to the problem. This, as I said, this is what we got by generating from the metamodel. And we program according to that grammar, and this is a program. It looks very ugly because you see the nesting is very deep, and there are lots of keywords and braces. Most of them are unnecessary. But why is that? As I said, it confirms to the grammar because grammar defines that. In the generated grammar, there are lots of things, for example, keywords, braces, commas, and many things that we want to remove or modify. So did our industrial partner. They also want to have nice textual grammar. So then, when we really try to optimize it, we find further issue. For example, here, we remove the keyword short name, and we want to also move the attribute short name exactly after the make keyword. This is aligned with our program habit. And the problem is that there are lots of grammar rules also have the same attribute called short name, and that means we should do the repeated modification of many grammar rules. So we want to automate it instead of manually work. And there are lots of other types of modification. For example, we want to change the orders of the attribute. For example, we want to remove the optionality. So we also think maybe there should be a method that can be used for other languages. So we need a general modification rules. And we also sort of a question, what if the meta model evolves, even maybe some languages evolves very fast? We need support to the evolution. So based on the issues, we developed a tool called a Grammar Optimizer. Maybe the name is not that good, but we call it Grammar Optimizer. And this tool take the generated grammar as the input and optimize it to be a nice one or to an expert created one. And it's based on many general rules for optimizing the grammar. And how to use these optimization rules, we have configured to invoke the public method of those rules. And here is an example of the configuration. We can see here it's about 22 lines of configurations, but it optimizes thousands of lines of text in the grammar text. And then it's about the goal of this paper. We sort of a scenario that a meta model is co-involved with an associated grammar. Here is a script map. We can see that first we have a previous version of a meta model. We call it M1 here, and it evolves to another version of a meta model called M2. And there is a grammar called G1, which is generated from the meta model. And we did some manual improvements to make it more concise or to more beautiful and get G1 prime. And now the requirements comes. We want to make sure that the grammar still align with the meta model, the involved meta model. So we generated the grammar from the meta model again. We got G2. And another requirement is that we want to have the manual improvements in the grammar. But we cannot just copy it. So we can use the grammar optimizer to do this. But the problem is that, as I said, we need to configure the tool. So the method here is to we compare the generated grammar and the optimized grammar for the first version, and to extract the configurations And we reuse the configuration to drive the grammar optimizer to optimize the generated grammar that is G2 here. And the extraction work is done by the tool configure generator. So how to do the work? The whole process of these methodologies that in the first step, we select some sample languages, and then we obtain the targeted grammar and the meta models of these languages. And then we develop the tool, we call the tool configure generator. We developed this tool according to the principle of the grammar optimizer, because the Lua configurations anyway will be used in the grammar optimizer. And then in the evaluation stage, we generate grammars from the meta model by using Xtext. Then from now, the generated grammar and the targeted grammar are all in place. So it's time to apply the configure generator. The configure generator takes these two grammar as an input and output the optimization Lua configurations. And then let's go into the assessment. The idea is that we use the configurations to drive the grammar optimizer to optimize the grammar, to get an optimized grammar. So then we compare the target grammar and the optimized grammar to see whether they are the same or they are different, or how many grammar rules are different. So how do we implement the configure generator? I wouldn't go too much deeper here, but I will go through simply. In the first step, we read the text of the grammar, and then we split the grammar into grammar rules and put each grammar rule into a data structure, and then we connect all the data structure as a list. So there will be two lists. One list is for the generated grammar and another list for target grammar. So then we traverse one list to fetch one grammar rule at a time. And we search for a grammar rule with the same name from another list. If we don't find it, that means there should be an optimization rule for removing the grammar rule in the configurations. If we found it, then we can just compare these two grammar rules. And this compare based on the line matching and line comparison. Then we identify the differences and generate the required rule configuration. And after that, we also check if there is any new grammar rule added. So then we complete the calculation of required optimization rule configuration. So then we write the optimization rule configuration back to a file. That's what we got, and this will be used in grammar optimizer. And here is a simple example of how the extraction works. For example, there is a line of an attribute from the definition of a grammar. The attribute is called an owned comment, and the left one is from the generated grammar, and the right one is from the target grammar. And we compare them, and to identify the different. For example, in the owned comment in the generated grammar, there is a keyword called owned comment, but there is no such keyword in the right one. So here we got to know that there is an optimization rule called a remove keyword is needed. So this is how, and here we apply the regular expression to identify the differences. And finally, we go to the results. There are many columns, but the most important is the right three columns. But here I also go through other columns. In the second column, it shows the lines of configuration that manually made configuration. And the third column shows the line number of the extracted Lua configurations. We can see that the extracted optimization Lua configurations have more lines than the manual one. And from 4 to 6, we show the how many grammar Luas should be changed or removed or add when comparing the target grammar to the generated grammar. And from 7 to 9, it is the result of comparing the optimized grammar to the generated grammar. It shows how many grammar rules have been changed, how many grammars have been removed and added. And finally, we compare the target grammar and the optimized grammar. And the result shows that there are 3 languages, ESLA, EDL, BibTeX, and XNet have the same grammar rules in both optimized grammar and the target grammar. But there are some grammar rules different in the optimized grammar and the target grammar for the 3 languages, DO, TX, Core, and SML. So there is some grammar rules are different, so there should be something missing. So what are missing and why they are missing? First, the line order sometimes matters. There would be some adaptation and modification change to the line order, then it will affect the calculation. And the second is a grouping of attributes is unprocessable for the moment because, as I said, our comparison is based on line by line matching and comparison. And if there is some capability that are missing in the grammar optimizer, then we cannot extract any Lua configurations for that because, as I said, the configuration, the configure generator is according to the grammar optimizer. And if there are many, for example, optionality in a same line, it will also confuse the comparison for the moment. And why it is still useful? Because this tool can help us to, we don't need to start from scratch, even if we don't extract all the required Lua configurations. You can continue that. And the speed is important. It still reduces a lot of time. And the conclusion of the future work, the conclusion is that the proposed method for the automatically extracting grammar optimization rules, which capture manual improvements from a previous evolution step and allow these improvements to be replayed in the future versions of grammar. Future work. First, we want to improve the coverage. As the previous page shows that some coverage still hadn't been 100%. So one idea is that we can move to our work to abstract syntax tree. Yeah. And we also want to do some work on the complementary co-evolution scenario. That means migrations of a meta model after changes to the grammar. And then we also want to apply the approach to a practical environment because so far the evaluation is based on some sample languages. And we are also thinking of the creation of a language workbench that supports blended modeling. So the proposed method will also contribute to that. Yeah, that's all. Thank you.
Thank you, and commendably to time. Do we have any questions? Could you come and use the mic because we're live streaming? Thank you.
Thank you very much for your talk. My question is that in the slide where it was like problem statement, you mentioned the configuration rules. So is configuration an input or is it something that you generate? And if it's something that you generate, do you have the initial grammar and the optimized grammar available so that you can generate configuration? Is that clear?
I'm not sure if I fully understand the question, but I can try to answer. The generation is that we have already many existing optimization rules which was developed in our previous work. That is the tool called a grammar optimizer. So then in this generation, we actually is to calculate what is needed, what is the needed optimization rules is. So with the calculated rule configuration still need to find the rules from our previous work. That is 60 optimization rules. So the generation is actually to match what the rules needed.
Right. Yeah. So if I repeat what you said is you already have that grammar optimizer from your previous work, so you generate configuration based on the optimized grammar that you have.
Yes.
Okay. Right.
Yeah.
Thank you.
Thank you.
Okay, thanks. Eric.
Thanks for your interesting talk. I was curious if you could maybe characterize the kind of rules in your previous work in the optimizer and how those rules are different than the ones you're extracting from the manual rewriting. Are they sort of fundamentally different looking rules, or?
Could you repeat your question?
If I understood right, you have the existing rules in the grammar optimizer.
Yes.
And then this work is about extracting more rules from the manually fixed grammar.
Yes,
right. And so how are the rules different? Are they similar, or are the ones you extract like specialized versions of the general ones, or?
Yeah, the rules they are similar, but they are different. They works for different modification purpose. But yeah, from the implementation level, they are similar.
Yeah, maybe I could ask you later, but I'd be curious to see like in examples of the different rules, if they're
okay.
Like, why did the general ones not fully solve the problem, and you needed to extract these additional ones? So,
I think that the optimization rules, we can freely combine different optimization rules from the whole set of the rules, and to do different modification. And it is very general, and we can apply it to many languages. But what I said, the coverage is not reached. In some languages, the coverage is not reached 100%. It's just about the generation.
So you get more coverage with the extra rules.
Yes.
Oh, okay. Okay. Cool. Thanks.
Okay. Any more questions? Well, let's thank the speaker again in the usual way. Thank you. Ready to go?
Yes.
Okay, so we have another talk on software engineering modeling now, on recommenders rather than meta modeling. I'm sure you can introduce yourself better than I can, so off you go. Thanks.
Okay. Good afternoon. My name is Lisette, and I'm going to be presenting reuse and automated integration of recommenders for modeling languages. This work is done together with Antonio Garmendia, Esther Guerra, and Juan de Lara from the Universidad Autónoma de Madrid. So here's an agenda of what I'll be talking today. First, I'm going to introduce recommender system and a little bit of the context where we're going to use it, the current situation we have, some challenges, the proposed approach, architecture and tool, and a conclusion in future work. So recommender system are software tools and techniques that suggest items that are relevant for a particular user. And as we know, these recommender systems today are available in Netflix, recommendation movies, and other sites for music like Spotify and so on. So in the context of model-driven engineering, here we have a class diagram. On this part here, the class diagram have a class professor, and here professor have two attributes, pretty simple, and in this particular moment of the developing of this model, the modeling engineer wonder what other attributes maybe want to add to this class. So from a data set of models that's conveniently stored somewhere else, so an algorithm use this information. I am so sorry. This algorithm use this information and suggest, wow, I'm sorry, and suggest, here suggests to add surname and birthday, considering that maybe this class is similar to the class saved in the data set of models. So basically, that's how it works, recommender system in model-driven engineering. And in this example here, to add extra information, the target could be university, in this case, a class, and an item could be the attributes. Also, it can be interfaces, for example, and the interaction between these target and item is what create an interaction with will be given the positivity that this target need or used in the past this particular attribute. So the current situation is that we have many recommender systems for modeling tasks. Here are some papers previously published where you can have recommender system for meta modeling and a core, recommender system for UML, using different algorithms like context collaborative filtering of NLP. So this recommender system, as I mentioned, they go for a variety of different recommendation methods. They are targeted to concrete languages, and normally they are developed for independent tools, and even sometimes they just get to the point where you do offline evaluations, but never is integrated to any modeling tool. So from this current situation, we have the need to integrate these recommenders that are not being used in action, or normally this type of integration take a high development effort. And currently, you cannot reuse a recommender system that is developed, for example, for a core to use it on UML-based modeling tool. So the big question is, can we reuse this recommender system for my modeling notation, and can I integrate them in my modeling tool? So we have here 4 different challenges for this. The first one is the target modeling language. As I mentioned before, we have some of them being developed for core, for UML, for other modeling languages. So ideally, we would like to know if we can reuse this in different notations. Second, the recommendation sources, they're coming from different places. Some of them are deployed in an API. Some of them are, you have to download and install it yourself. Number 3 is the recommended items. Sometimes they recommend, as I mentioned before, attribute for classes, but they can recommend packages to other projects and so on. And finally, the modeling environment. Some of them are deployed, some of them are not deployed, or some of them are deployed for a specific modeling environment. So before I go to the proposed approach, I'm gonna depict this dimension that we did to explore how we can do this reuse and integration. So first, we have the target modeling language. As I mentioned before, it can be homogeneous if it's for the same modeling language that we're going to use it in the same one we develop it, or if you're going to use for a different one, which is going to be heterogeneous. The recommendation sources can be local, if it's just directly in your Eclipse or your framework, or remote if you can access through a remote service. The recommendation items, it can be for multiple targets. You can have different targets at the same time, different domains. Sometimes these recommender systems for model engineering that are domain specific are developed for only bank domain recommender system and so on. So you maybe have multiple domains. And finally, the aggregation rank. If you have the same type of item being recommended for a particular target, you may need to rearrange all those recommendations if you aggregate multiple recommender systems. So for this one, you have supervised and unsupervised, and unsupervised have majoritarian and positional. And finally, the modeling environment. Here, which is the detail you're going to use it. It can be graphical, textual, or tree-based, or the interaction, if the recommendations are going to be reacted, if you have to ask every time you want a recommendation, or proactive if the recommender system can know where in the active model you are, so it can recommend something appropriate. So our proposed approach is a Eclipse plugin called Ironman, which means integrating recommenders for modeling languages. It's for the reuse and integration of recommenders into existing modeling tool. And Ironman guides you on the discovery and selection of recommender system, adapting to different notation if it's needed, configuration of these aggregation methods for how you're going to re-rank the recommendations, and finally the deployment on, for the moment, serious and tree-based modeling tools. So here we mark the ones that we currently support in Ironman. So first, for the overview of the methodology, this work is supported in our recommendation service API. Here we have two. The recommendation service indexed is the one where we're going to register all the different services, and the recommendation services is the one that these registered services have to comply to the endpoints designed there in order to work with our methodology. So first, Ironman, you have to select the recommenders available. All the recommenders or recommendation services that you had indexed previously are going to show here. You're going to select the one you need. Then you're going to select which targets and items you want to use. Afterwards, you have to adapt it to the modeling languages if the notation is different from the one that was conceived for. Then you select the aggregation method if, as I mentioned before, you have similar item types for a particular target. And then you configure the modeling tool or the detail you want to deploy this recommender on. And then you go for deployment. And finally, you have these integrated recommenders on the modeling tool. So just for a quick view of how these endpoints work, it's very simple. The recommendation indexer basically have two endpoints for register and update this registration. And the services in Discover is the one who allowed Ironman to access to all these recommender already indexed in order to connect it to the Eclipse. And the recommendation service API, which is the one who the recommender have to comply with. It have two endpoints. One is called features that have to contain all the metadata that we need. So for example, in this case, we have here in the A section, this is a class diagram, as we saw before, and this is how it's going to be encoded for JSON for our tool. So here, for example, in this case, the E-class is the target. Here we have the target features. We have to specify which is the right property, because a lot of these tools or tree-based tools and series-based tools, you collect information from one place, but then you need another way to access to write this information. So we make a difference between which is the reader property, this will be the read property, and which one will be the item in which the item feature. So all this information here is encoded in this base. So all the recommender systems or recommender services that you want to index have to follow this particular endpoint. And the second endpoint is the one for the recommendation. So here you have recommend with a name, and then this is some query parameters that you can use. So basically here, for example, you have a current scenario, an active model that you're working on, similar to the one we saw at the beginning. And this is the encoding that you need to provide for requesting a recommendation. So using these two endpoints, then the rest of the work is done by Ironman. So for the adaptation, there is more detail in the paper, but if you see here, we have a pretty simple adaptation for the different annotations. Currently, we are working with notations that are quite similar between the target and the source of the recommender, but we want to work in the future with more complex ones. Here, if you see, we are mapping, for example, an E-class is equal to a class, and then name to name. Here, a structural feature in the write property is on attribute. E-all attributes in the read property is all attributes. E-attributes correspond to property, and name to name. So it's a structure per server mapping. This is quite simple, as I mentioned before. So, but the idea is that we are mapping where each one of these recommendations from the one that was designed for is going to go to. And for the aggregation method, also we have 3 different aggregation methods. This example here is for one that's called board account, which is quite simple. Also, here, for example, we have, imagine you have 3 recommender systems from different notations that are recommending you different things for a particular class, for example. So these 3, you calculate different scores based on their positions and if they repeat between themselves. And finally, here you have a summary of all these scores. And depending on the tool you're using, you may want only the top 5, top 10 recommendations, then those will be returned. So for the architecture and tool support, as I mentioned before, here Ironman will be communicating directly to the recommendation service indexer through these 2 endpoints, which is the one who allowed to see and discover which recommendation service had been deployed. We also have to work from the support of the meta model of the recommender and the meta model of the DSL. So all this work is done for Eclipse. So you need to have installed, all these meta models support in order to have it available in Ironman in order to do the mapping, for example. So here we have 2 extension points. One for the aggregation method. As I mentioned before, we have board account. Also, we had our ranking and media rank aggregation. Here, also, we want to explore in the future with more aggregation methods. And also, we have another extension point for the modeling tool or the editor we're going to use. Here, we have support currently for Treebase and Civio editor. So here, through, in the case of Sirius, both of them actually go directly request of the recommend through the recommendation services API. And in the case of editor, they go to the recommendation system layer, which is a layer provided by Sirius, where we inject these recommendations. And in the case of the Treebase editors, we directly inject it in the menu. And in these cases, all of these integrations are done without source code or anything. It's just using the layers of the menu available in the different tools. So I'm going to make a simple example of how to use the Ironman. And in this case, we're going to showcase a little bit of how to integrate 2 different recommender systems for 2 different notations and different tools. So the first one, we have the recommendation system selection. So here we have 2 recommendation services already indexed. After we index it, all this information is collected through the features endpoint that have all the metadata. And here we select which recommender systems we want to use for this case. Second is the item selection. So here, after we select the recommender system, we see here the recommender system we selected and which are the items are available. In this case, all of them have available attributes and operations. The third one is adapting the recommender system. As we saw before, some of them are in the core and some of them are in UML. So the ones who are in UML, we want to adapt them to a core because we're going to use them, all of them, in a core-based recommenders. So here, for example, as I mentioned before, it's simple. You can look here in Add Modeling Language. You look through there that you have installed the meta model of the UML in this case, and then you're going to select which one is the one who's going to adapt to. So that way it's going to be automatically integrated there instead of the original where it was deployed. The fourth one is aggregation of recommendations. Here you just choose which algorithm you want to use for this aggregation. Then is environment selection. Here you have to choose from the environment available which one you want to use to deploy this. Here we select both of them, Sirius and Tree Editor. In the cases the tree editor, you don't have to do anything. It's only have this menu layer available, and it's gonna go directly to where you have to go. But in the case of Sirius, we have to choose the diagonal representation and do another selection for this particular aggregation. And finally, the deployment. So here is how it will be deployed. We have a couple of images. For here, this is the integration in a core tree editor. So here you can see a regular core tree editor, and when you select the recommendation, you can see where it's coming from, what is the rating to have. This rating is coming after the aggregation, because if not, it will have the score from the original recommender system, and which are the recommendations that you have. In this case, this is a Sirius editor, it's a specifically obey UML designer. So here you can see also where the recommendations are coming from and which type of recommendation. You select what you want, and it's going to be added automatically to the class diagram. So for the evaluation, first we want to see if we can adapt this recommended system to different languages, and if we can integrate it into third-party modeling tools or existing modeling tools. So for the evaluation, we use two recommender systems, one for core meta models and one for UML class diagrams. We use it for 4, meaning other 3 different languages, each one of them to use one of these ones. And also, we integrate it in different modeling tools. So here, this is the experiment results. First, here we have how many integrations we did, the recommender system of the original recommender, the language of the original recommender system, the language we adapted to if there was an adaptation needed. Here, as you can see, it's from a core, so there is no adaptation needed. Then the editor we integrated, and how many line of codes was automatically generated for this integration. So if you can see here, there are 0 maps, because for these there is no mapping need. But then the other ones are from 5 to different 9 mappings, depending of if the tool supported attributes and operations, or if the tool only support operations alone. So these are images from this evaluation integration. So if you can see here too, this is a core tools. So these, as I mentioned before, automatically create this here in the menu that's called recommender, and then you select which type of recommendation you want, and then you can see this information here of all the recommendation items. And this is another example for UML3 editors, basically the same. You have somewhere in the menu a recommender when the options that you can automatically use in your modeling tool. So to answer the different, the 2 research questions, if we can reuse or adapt these existing recommender systems to different languages, the answer is yes. We reuse them for a core, UML, entity relationship, and EFML. And the only requirement for these was the mapping that can come from 0 to 9, depending of the particular case. And if we can integrate an existing recommender system, existing modeling tools, and the answer is also yes. So we integrate this in 6 different modeling tools that are based in Sirius and EMF. And as I mentioned before, all these integrations are with third-party modeling editors, and we did not need to access to the source code for these integrations. So as conclusions, we have proposed an approach to reuse and integrate recommended systems, and name it Ironman, based on a common recommendation API, mappings bridging the recommender system and the modeling notations, and rank aggregation algorithms. So Ironman is able to adapt and integrate recommended system within Eclipse modeling tools based on Sirius and 3 editors. So for future work, we want to integrate this aggregation that I mentioned before that have board account and all this algorithm, till the moment don't provide any benefits. It's only a way to re-rank, or the benefits are really not much considerable. So we want to investigate more on using other type of aggregation algorithm that can actually improve the recall, the precision of these recommender systems. We want to extend our proposal using supervised rank aggregation methods, as we only work with unsupervised aggregation methods. We want to support integration with text annotations, such as xtext. And we want to explore other types of integration, meaning that currently you have to request every time you want a recommendation. So we want to also provide proactive recommendations during the modeling. Thank you. If you have any questions, this is the moment.
Thank you very much. Do we have questions? Could you go and use the mic in the middle so the live stream can pick it up?
Okay, thank you for the great presentation. I have a question about the context that Ironman is sharing with the recommendation system. So with recommender system, it's very important to know the clients. Probably you and I have very different recommendations on Netflix. So when you're asking for a recommendation, for instance, for the professor class, what is the context that you share with the recommender system? Is it the entire modeling language in which you have the professor class, or is it just the professor class, or is it something else?
Actually, because here I'm only reusing already deployed, already designed recommender system, but the thing is, I didn't put everything because I didn't want to put too much technical thing. I just wanted to go light up. But here, sorry. Yes, here, I work with, if you check in the paper, there is like a meta model that serves as everything that is compliant to this idea. And here you see the context. So here you have already to explain which type of content you're expecting from your recommender, because every recommender, as you mentioned, is different. So we already support 3 different types of contexts. One is targets, which is the target, everything the target have, and everything of the same type of the target. None, if you don't request anything, or full, if you request everything that is happening within the modeling context. So that's the coverage we have in the model.
So is it in the configuration of the recommender system that the recommender system itself says, I want the full context, or I want nothing, or, okay.
Yes.
So it's part of the configuration of the recommender, and Ironman just adapts and gives the expected information.
Yes, there is still, this is the first paper we have in this tool. So it's kind of basic, covering everything that we consider. That's why we devise the dimensions. But right now, like this feature endpoint and the recommendation endpoint are pretty vital, that the one who wants to use it follow them and use the correct information and know what is correctly expected. So there is a lot of assumptions that we won't know everyone what we are doing. So of course there is a lot of work to do there to be more ease on the user. But yeah, in the moment you have to specify and then also know that at the moment of the use of the tool.
Okay, thank you.
Very much.
Okay, any more questions? Okay, let's thank the speaker again in the usual way. Thank you very much. Well, we're keeping commendably to time. This is most impressive. Let's just wait for Francisco to get plugged in. Did we lose the cable?
For an HDMI cable?
Yeah, it's here.
Oh my God,
Okay. Right, okay, so final talk of the day, and this is the other kind of modeling, the one that one hears a lot about these days, large language models, GPT-3 in this case, and can it help you with your type error debugging? Francisco, thank you.
Okay, so can everyone hear me? Okay, so I'm the intruder that got into a modeling session without a modeling paper. I guess the model's keyword there fooled the segmentation algorithm that distributed our presentations. So, hello everyone, my name is Francisco Ribeiro. I'm a PhD student at the University of Minho in Portugal, and I work on fault localization and automated program repair. So, and I'm here to present our paper with the title GPT-3-powered type error debugging, investigating the use of large language models for code repair. A rather long title, but that's what ChatGPT told me I should name my paper, so I didn't even question it. Which describes a work done in collaboration between the University of Minho and the University of Porto, both in Portugal, and NII in Japan. Okay, so to begin with, let's briefly talk about what a type system is. Programming languages usually have a type system, and these assign types to terms in a program. Type systems also determine if some operation can be applied to some term in a program. And this way, type systems ensure a program's correctness regarding type safety. So that is, if a program does not type check, then there's a logical error related to the type constraints. And here is a very simple example, just to showcase what we are talking about. So adding 1 and 2 makes sense. It works, that's 3. Adding 1 to a string word does not work. That is, it does not type check. And so we get an error. Specifically, we get a type error. And notice that the message mentions some types here. And that's because we can also have type inference systems that compute expected types. Furthermore, compilers also try to locate the fault. They try to tell us where the error is. However, compilers often fail to pinpoint the true cause of the error, and that's the motivation for this work. This is an example of a recursive function in OCaml. So this is the part where my supervisor turns away because he has to look at OCaml. And I can't because I'm presenting. And it's the addList function, and it takes a list of integers and should calculate the sum of all numbers. There is some pattern matching going on regarding the input list. If the list is empty, an empty list is returned. Otherwise, we add the current element to the recursive call on the list's tail. So indeed, the compiler detects an error and provides a message about it, highlighting the problematic part of the program. It does not know how to add something of type list of the sum A. Replacing the plus operator with the cons operator, which inserts an element to the beginning of a list, in fact, makes this program well-typed. But this is not the true origin of the error. The message we get about mismatching types does not guide us directly towards the issue. Another way we have to fix this type error that actually corresponds to the programmer's intended fix is to replace the empty list with 0. And by doing that, we have a well-typed program as well. Things to take away from this. So the intended modification can be different from what the compiler reports about. The order of expressions influences the reporting of type inconsistencies, and that is because as long as no inconsistencies are detected, expressions are considered correct. In other words, type systems have a left-to-right bias, which tends to make errors show up towards the end of a program. And notice that swapping the two patterns changes the reported expression, which essentially means there are multiple causes for this error, this type error. So what is our work? Well, even after recognizing these limitations, we still have to fix the error. That is, even if we know what part of the program was faulty, we still had to come up with the change for it. And automated program repair aims to fix programs with as little human intervention as possible. And that is where we focus on, automatically finding repairs for type errors, because we argue that doing that is an effective way of locating them and understanding them. So the way we do this is by analyzing and manipulating the source code of ill-typed programs to generate something called prompts or inputs, that are then provided to GPT-3 so that we can leverage the model's code understanding and code generation capabilities. And our aim is to produce programs that are not only free from type errors, but also correct according to the original intent. We shall see how we also work on this. So just to make it clear, this is where we focus on, that highlighted part in red. The main idea is that good quality prompts provide good quality generations. So therefore, efforts should be placed on building the best possible prompts. Models are not magic. So we need to actually make some effort into giving them good inputs so they can give us good outputs, good results. What is our technique? So for an OCaml program with a type error, we extract as much information as possible from it, and we format that information to build good quality prompts for GPT-3 in this case. And to do this, we perform 3 tasks on the source code. Type error location, inlining, and type unification. Okay, a lot going on here. OCaml provides a function called magic in the OBJ module, which has type A to B. And when you see A and B with those apostrophes, it's a way to have a polymorphic type in OCaml. And that magic function converts a value of any type into a value of any type. So in other words, we trick the compiler into assuming an expression of one type has, in fact, a different type. So if you hear me talking about typecasting something, it means applying this magic function to something. I may use those interchangeably. And if we recall the introductory example, and the 2 places, we try to modify to fix the type error in the addList function. When we apply magic to the empty list, that first listing there, it gets converted to a polymorphic B, and the compiler deduces this to be int. On the other hand, we can also apply the magic function to the plus operator, and the compiler deduces this to be a function with type A to list of A to list of A. What is important to retain here is that every application of magic, this magic function, that makes the program type check, is a candidate for type error location. And in this example, the first 2 would be candidates because they type check, and the third one would not be a candidate because even though we apply magic, there's still a type error in the program, so we don't consider it to be a candidate to fix. The second task is inlining. We make use of inlining not for the usual purposes of compiler optimizations, but to be able to make information available from some parts of the program in other places. This program here applies operators that are incompatible. It's a very simple illustrative program. It adds X to itself, and it also applies a logical AND, but in prefix notation. And if we consider this program, which has a type error, and we typecast this expression, that is, we apply magic to that logical AND, the type error goes away. And the intended type for that specific part ends up being int2 A. However, if we extend the program with a very simple test case, f1 equals 3, we inline that usage of f, we associate it to a different context in which the type system knows more things, has more information, knows that int there. And if we perform type inference on that second occurrence of f that we just inlined, we get a more specific type. And that way we can get more specific information about possible types. And we can build more useful prompts. That's what we want. We want extra information to be able to build useful prompts. And the last task is type unification. We make use of type unification to filter elements from a list of completion suggestions. Basically, we replace the typecasted expressions with something called typed holes, and we then ask for completion suggestions on these typed holes through, so a typed hole is represented by that underscore, by the way. highlighted in orange. And on these typed holes, we, through something called the OCaml LSP, which is a language server protocol. It's a technology many code editors use in the background. We use it programmatically, so you can interact with it programmatically. This is just for illustration purposes. And we ask a list of suggestions for that typed hole through OCaml LSP. And we also perform something called type inference on these typed holes. And what we then do is that we apply type unification between that inferred type and each suggestion in the list. Because these suggestions do not necessarily match the expected type. And in this particular example, we are able to reduce a list of 318 suggestions to 23, because the majority of them didn't actually fit the type that was expected there. And based on everything we talked about so far, we implemented several repair strategies. This is the part where our approach actually tries to build patches that will fix type errors. And the simplest one is called fill. We called it fill. And what we do is each time we detect a candidate location for repair, that is when using the magic function makes the program type check, we just replace that expression with an insert tag. This is the simplest approach. And we then make use of GPT-3's insert mode that exists, is available through an API, and we ask for a completion. So in this case, it's actually able to just put the 0 there, which is actually what we want, simplest one. But, and we also developed some more elaborate repair strategies. This one is called choose. And it formats, actually perhaps the most curious one, it actually formats the input candidate program as an exercise, similar to what you may find in an exam, for example. So the template for the exercise is presented as the source code with a missing hole denoted by the mask identifier and a list of possible solutions, which we obtained through that type unification task. And we then ask GPT-3 to select the most appropriate option, but we guide the model into selecting one option through something called prompt engineering, which is actually really important, because you will get a lot of unpredictable stuff if you don't do it. We do this by preceding these prompts with 2 example exercises that share this template but are already solved. And laying down that structure helps the model understand that it should select one option and it will actually focus on just giving me the letter I want. In this specific example, the correct choice is not present, but it was a very good example to illustrate that there are some disadvantages with this, and it was succinct enough to illustrate. And the last strategy that uses GPT-3 is called instruct. This uses something called an edit mode, and this is the most different from them all. It expects 2 things, 2 inputs, the prompt, and separate instructions describing how to edit the prompt. And we perform those inlining and type unification tasks on the magified typecasted program in order to compute the minimal substitution for that expected type in the underscore. And we wish to see that hole filled in, and the template we use for the instructions, there in the bottom of each example, the template we use for it is replace the underscore with something of type whatever was inferred. In the first case, the inferred type is int, and GPT-3 indeed responds with something of type int. It will fill in the 0 there, right, which I didn't put it here, but it does. And the second one does not correspond to the candidate that will generate the fix, but it still serves to show something very important, which is creating adequate prompts is essential. Because in the second example, the inferred type is of a function. So A to list of B to list of B. And if we submit this to the model, it will in fact answer back with a function. So it won't, in theory, it could completely disregard our instructions and just realize that it should place a 0 like it did previously. But no, it actually takes our instructions really seriously. And it will try to actually place a function there. So that actually shows that effort in building the prompts heavily influences what we get out from the models. We also implemented a completely offline strategy. This was a consequence we did not predict, but it means we can actually skip interaction with GPT-3. This is not the focus of our work, but we will still briefly talk about it. After locating some candidate expression with that whole usage of the magic function, and you compute a list of suggestions, just like we did for that repair strategy that tried to emulate a programming exercise, choose, we actually try every computed alternative, and if it passes one or multiple provided test cases, we will simply report back to the user that this may fix your program. And to test our approach, we conducted a large-scale evaluation. We used an existing independent and public repository, originally with 4,500 programs. And for each, we had a type error version and a fixed version. And we filtered out programs that needed multiple modifications in disjointed places, more on that afterwards, and programs for which the fixed version did not pass some quick check tests, and we shall also see that. So if the reported fixed version did not pass the 10,000 generated quick check tests, we assume that that is not a fixed version, so we also filtered those programs out. And with this, we end up with 1,318 programs to analyze. And our strategy before getting on to the results, our strategy to validate the generated patches is fully automatic. And it is flexible to allow patches that are equivalent to the intended fix without any human intervention. So for each patch, we instantiate the following template quick check property. We provide the input signature of the function to implement, for quick check to implement, or rather to use the appropriate generator, generate the default value of 10,000 inputs. The output signature tells quick check how to compare results, and the property that should be verified is that the result of the original fixed version should be the same as the result of the patch that we are currently testing. And if this holds, the patch is considered equivalent to the fixed version, and thus we consider that that is a successful repair. So as we said, we analyzed 1,318 programs. 516 were completely fixed, and that's 39.2% of them, and 441 were partially fixed, which is a 33.5% rate. Partial fixes are patches that satisfied somewhere between 1% and 99% of test cases. This actually allows us to explore the ground that separates a completely fixed program from a program that remains broken. It's interesting to see that there are actually some amount of programs there. Another way to look at the data, so 361 programs remain unfixed, with 247 of them erroring out, 73 had no patches generated, and 41 actually failed every single one of the 10,000 inputs, it failed. So these were especially challenging bugs. And what we also notice is that it is more likely for a program to be completely fixed, which is those 516, or remain unfixed with 0% of test cases. So it's more likely that the program will fall into one of these categories. The partial fixes are in a lesser quantity. We also analyzed the effectiveness of each repair strategy that we devised, the ones that use GPT-3. Fill is the most effective one. It's also the simplest one, so sometimes simple is better. And followed by instruct and choose. Some programs are fixed by only one strategy, whereas some other programs are actually fixed by multiple ones. It's worth noting that although choose, that smaller circle there, is the least effective strategy, there are still 30 programs that are only fixed by it. So then, for example, on the other hand, 24 programs are fixed by all the strategies. All the strategies can reach the intended fix. We also conducted a comparative study between our tool called Mentat and two other type repair tools for OCaml, which are Write and Seminole. The three tools use a common dataset, and each apply its own pre-processing criteria. So as a consequence, the dataset was filtered to 591 programs, which were the programs that were common to all three works. And out of these 591 bugs, our tool is Mentat. It fixed 222, Write fixed 198, and Seminole fixed 46. And some of the insights we take from this are that Mentat surpasses existing state-of-the-art tools. We were able to fully validate results from Write, whereas initially the authors reported a manual analysis of 21 programs. Passing tests is different than type repair. Tools normally have a higher rate of type repair. So for example, Write reports at least 80% type repair accuracy. Our tool is also able to produce more patches that fix type errors, but when we consider test cases, these numbers go down, which actually contradicts the informal saying in functional programming. That is, if it type checks, then it is correct. Turns out GHC and OCaml-C are lies. So, to finalize, we automatically validate all three approaches. Our technique, Mentat, is based on a language-agnostic approach. We wanted to focus on this near the end. So it has two requirements. We need to statically determine types of terms, either through type inference or annotations in the program. And the second requirement is that we need an ability to bypass the type system. So all that long and weird stuff about using a magic function and typecasting, which would be the equivalent to Haskell with the undefined. It's just ability to bypass the type system. And moreover, using large language models, in this work we happen to use GPT-3 for patch generation, trained on multiple languages, liberates us from building language-specific generation systems. And to finalize, for future work, we would like to experiment with other large language models, for example, GPT-4, but especially open source alternatives that are coming out and are especially powerful, like Llama 2 and Code Llama from Meta. We would like to expand this work for type errors that need fixing in multiple locations, that need some restructuring of the technique. We focused on single location bugs, mostly single location bugs for now, to validate all this. And we would also like to explore model fine-tuning, either for OCaml, other languages, but especially specific contexts, like fine-tuning models for program repair, for example. And yeah, that's it. That's all I had to say. Thank you, and please feel free to ask any questions.
Excellent. Do we have any questions for Francisco? Vadim.
Cool stuff. So one of the things that GPT is known for is confabulation, basically producing things that are totally believable. They should be there probably, but they are not. Right? So for instance, referring to, I don't know, a function that should have been there in the library. It's very sensible to expect it there in the library, but it's not there. So it's
in the generation, it's not. It doesn't show up in the result.
What result?
Yeah, go on. I'm still trying to understand the question.
Well, you make a request to GPT to either through a chat interface or the way you are doing it, and you're saying, please give me the code or fix this code.
Okay.
And it fixes this code in a way that should have worked, but because the library has been not complete or something is just not there. Right? Have you encountered that in your setup, and how do you propose to deal with it?
What we noticed is that less context usually leads more to, we didn't specifically study that, so this is kind of informal observations, but we noticed that more context helps those situations occur less times. But yeah, there's always some degree of unpredictability to what could come out. So yeah, if doing this is wrong, fix it, usually it's more likely for those things to happen than this is wrong, this is the message I got, these are the types I need, some functions. It tends to happen less often.
Thanks.
very interesting work. Yeah, just kind of a comment. I guess you kind of touched on this in your future work, but yeah, I mean, it seems like what you're trying to get GPT-3 to do is basically a language modeling task, which, I mean, LLMs are really good at, but it seems like kind of a roundabout way going through a prompt asking it to fill in a mask token. It's like somewhere else you define, say, predict which of the following options. I mean, I was curious if you looked into using a more specialized model that's like trained on OCaml code. In my experience, you can do pretty well at predicting type information and things just by training on like a corpus of a few million examples of code and not having a LLM, but like a more specialized model, and just masking off and having it predict.
Yes, the main purpose of this work was to develop a technique that would be generalizable. So although we discussed it, we never had the intention of specializing in languages, because we just used OCaml simply because the person supervising this work from the beginning just said, we're going to work with OCaml, and I used OCaml. So we actually emphasize the idea of language agnostic, because we actually want this to be like different pieces that you can abstract as much as possible, and you don't have to specialize. Okay, if you really need to specialize, then you have to kind of have a compromise, but we are not looking for that. We want it to be as general as possible. So yeah, we did not look into specializing it for OCaml, for example.
Yeah, sure, yes, that makes sense. I mean, even if you are interested in trying to be more language agnostic, I guess my point was more, it seems like kind of a roundabout way of asking the model to fill in what should go in the token. Or like, have you looked into prompt tuning at all? As a
prompt tuning?
Yeah, the approach where you have basically a smaller language model that is stuck on the front of your encoder in whatever language model you're using, and you train that.
Yeah, again, we are trying to use models as out of the box as possible. We have the intention of exploring, for example, fine tuning and prompt tuning, but we would like to make use of these new tools as out of the box as possible, because that increases generalizability. We don't want to specify to any context or scenario as much as possible. We recognize we won't be able to do it every time. That's why we discuss it, we think about it. For now, we want to avoid it, because we would like for ideally some framework that would kind of give you some abstract elements you should have, and you can recreate this for your context. It's not that you have to come up with a new approach or technique every time you have a new language, a new platform, a new scenario.
Thank you. Yeah, I'll chat with you after.
Thank you.
Okay, who's next?
Excellent work.
Thank you.
Really excited. I want to use it for a language that we work on. I'm curious about what you think is next, because 33%, or was it 34? Something like that.
Oh, the rate, so...
yeah. The accuracy rate is really impressive, but I wonder what users will think was something that's wrong most of the time. So do you think what's next is increasing the percentage? Do you think that's possible, or do you have other next steps in mind?
We are especially interested in trying other models just to see if... So this is really interesting, because there's something called emerging properties that are things that just showed up in this scaling up of models that you can't actually predict, because they show up just because the model scaled up, or at least the knowledge so far that we have. We can't predict. Something that usually was done was you had smaller models and you would try to kind of predict how it would evolve if I had a model 10 times bigger, and that would help developers know if they should try to build the model that way, but simply bigger. But some things started to happen. That was when models got this big, they started to give generations that could not be predictable. And we are actually curious in using other models, not just because they're bigger, but also because they are trained differently, because we want to see if generations are actually better, worse, better for some things, worse for other things. but especially we always say we focus on this. It's because we actually did several trial and error things, just prompts we tried that will have generally bad results. We curiously happened to kind of stumble upon this, okay, exercise pretty fun, it's able to select an option. So it's like a creativity here, there's a big space to explore. We are especially interested in exploring the part where building prompts, yes.
Thanks.
Okay, thank you, thank you.
Okay, do we have some more? Yeah, grab the mic.
Yeah, just a follow-up question, because we realize there are still like over half of the benchmarks cannot be solved. So did you like inspect some of these manually to understand, why they are so hard for your tool, or maybe including the other tools, so that they cannot fix such programs, and what kind of features or patterns they have shown?
Not much, honestly. What we noticed is that so some of these programs were obtained in programming classes, and they are going to be really good at exposing common issues when people are either learning or just writing programs. But inevitably, even if the data set is a bit curated, you always have some weirder patterns that you start to question if they are that frequent or not. And those edge cases tend to be tricky.
Maybe
but
some of the benchmarks cannot be fixed. So is that the case? And some of them
can you repeat, please?
Yeah, I mean, some of them cannot be fixed. So is that the case?
No, we were not able to. They are fixable. The tool just didn't automatically generate the patch. Yes. There's a solution. But yeah, honestly, we didn't look into them mainly because we didn't have resources to manually explore each one of those. We put a considerable effort here because we were always stuck on the part where, okay, we have thousands of programs, we generate even more patches, but we need to know how does this make sense? Is this working? What's the progression? And this was actually a lot of work to have this done. The consequence is that we can actually grow the number of things we can analyze. Another consequence is that it's harder to explore the programs that are not fixed. I agree. It's one thing we would like to do. Again, we looked a bit into it. We noticed that edge cases tend to be really tricky, but I would like to comment more. But
given that you said that some of these patterns are maybe only made by programming novices, so maybe
or maybe not. That's why I don't want to commit myself too hard on this, because it may actually be common, and there's a problem with the technique.
Yeah, so maybe it's like an open question that still, can we have some benchmark that is more from the real world programs, like the real developers, they made this kind of type error. So but I know that this is really hard to collect, because when you want to conduct evaluation, it's really hard to find some, very fair and open data set that can actually, really evaluate things. But student assignment is something that's easier to collect, but but that the results are somehow a bit biased, right? But it's, it's hard to solve this problem. We can only use this as more like a
three things. So the focus of all the automated program repair thing is that it's based on something called I was trying to remember the phrase exactly, but it's like programmers do one thing really well and we never take advantage of it, and they tend to write programs that are almost correct. And models are really good. They're already really good at generating full programs or almost full programs, but they are especially useful when you have a clear, very well-established idea of what you have, and it's actually good at generating the part that's missing, your little fault. Second thing is that the programs were obtained from programming classes, because if motivation 1 was this, motivation 0 was that the person that suggested all this was working with students, and she noticed that they had lots of troubles with messages from compilers. She wanted something to help them.
It would make.
Yes.
Okay, so we're getting close to the end of the session. I think we'll wrap this question up for now. Is there anybody else who wants to chip in at this point? Okay, right. Well, I don't know if there are any. Oh, right. One more. I think this will have to be the last one today. Let poor Francisco out from behind the lectern. Far away.
Thank you. I wanted to ask if you explored how big the context of the source code should be, and does it influence the accuracy of the output? So there are languages, not like for Camel, that is pretty compact, but like Go, for example, where you can have a lot of code written in one function, and for example, renaming or changing some statement can be really can be lost in this huge context. So how does the size of the code impact the result? Thank you.
Bonus slides. Okay, just to address the question really quickly, these were some initial experiments. I won't bug you with details, but this set of programs, it's simple, it's really small. This set of programs, it's bigger. And what you notice is that, so really quickly, 87, 53, 87, 60, you increase the complexity of the programs and you get, sometimes you get better results. So increased size may mean more context, better generations. In the paper, I also report a bit about the size of the programs. I did not write it down in the slides, so sorry. I can refer to it later, but I don't have the numbers right now on me. Thank you.
Okay, lots of interest in large language models. Let's thank Francisco for his marathon question session. Thank you very much. Okay, now I don't know if there are any final announcements from the organizers or the program committee. Nothing? Okay, right. Then I draw the first day to a conclusion. We'll see you all tomorrow. Thank you very much. Bye.
Yeah, I feel you were not satisfied with scribbles as part of available learning by studying and presenting this in GPT space on legacy. So one thing is they tend to like to explore 3.5 and 4. They don't have types. I noticed greater emphasis in GPT-10